Mas, minta tolong mas, pindah dulu mas ke depan. Dua, 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 tiga, tiga, dua, tiga. Cek dua, tiga, tiga, dua. Apa lagi? Satu ya? Ini mana? Cek.
Tes, tes, tes. Satu, satu,
Bilang satu. Cek, cek.
satu,
Satu, satu, satu, satu. Cek, satu. Empat, 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 empat. Cek, empat, empat. Turunin dikit. Empat.
Om Swastiastu, Namo Buddhaya. Good morning and greetings to all of us. It is a great honor for me to welcome all of you to the guest lecture series of the Renewable Energy Skill Development, RESD program. Today, we gather to strengthen the educational partnership between RESD and Polytechnic Negeri Jakarta. I am Naura as Duta PNJ Batch 4, and it is my privilege to serve as your master of ceremony for today's event. Allow me to extend a warm welcome to the Honorable Director of Polytechnic Negeri Jakarta, Mr. Syamsu Rizal, along with the Vice Directors of Cooperate, the Honorable Mr. Thomas Gross, Chartered Engineer in Geomatics, Science from ETH Zurich, the Honorable Mr. Martin Stolt, GFA Consultant for RESD, and all the representatives from the team. The Honorable Head of the Mechanical Engineering Department, Mr. Muslimin, along with structural members of the department, and all to the distinguished guests whose name I may not mention one by one, but it doesn't lessen my respect for each of every one of you. First and foremost, let us express our deepest gratitude to God Almighty for His blessings and guidance that allow us to be here today. Distinguished guests, to show our respect to our homeland and our neighboring country, let us sing the Indonesian national anthem, followed by the PNJ hymn and March of PNJ. Ladies and gentlemen, please kindly stand up.
Sepanjang masa semangat jiwa dan raga sebagai insan yang berbudaya, kami berjuang sekuat tenaga mengembang tidak mau berubah diri. Hidup sama-sama kami berbuat iman dan terus berjuang membangun Indonesia jaya. Segenap sivitas akademika, janji setia, amalkan segala itu, jujur sampai lima, mengangkat citra ibu pertiwi. Bersama bersatu membangun membangun Indonesia jaya. Segenap sivitas akademika, janji setia, amalkan segala ilmu, jujur undang-undang dasar 45, mengangkat citra ibu pertiwi. Bersama bersatu prestasi gemilang, kerja sekuat tenaga, disiplin gali ilmu dan rekayasa, tunjukkan sebagai pemuda yang terampil, mandiri dan profesional. Sikap pegang sebagai mahasiswa yang terkadang berbeda macam. Bersatulah kita, ayo bangkit, janganlah tertinggal, maju, ayo maju, putra putri bangsa, ikrar mengangkat citra Indonesia. Kita jauh dibimbing serta dibina, membentuk sumber daya manusia yang berintegritas dan berpikir maju, mengangkat tidak perguruan tinggi, berdaya budaya bangsa. Bersatulah kita, ayo janganlah tertinggal, maju, ayo maju, kita putri bangsa, ikrar mengangkat citra Indonesia. Kita Dibimbing serta dibina bentuk sumber daya manusia yang berintegritas dan berpikir maju, mengembang dan pertumbuhan ini, memperdaya budaya bangsa.
Thank you, and please be seated. To begin the event, let us listen to the welcoming remarks from the person in charge of this event. Please welcome Mr. Yuli Mavendro to the stage.
Thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Previously, I'm sorry, I will speak with bahasa. Yang terhormat Direktur Politeknik Negeri Jakarta, Bapak Dr. Samsurizal SEMM. Yang terhormat Bapak Ibu Wakil Direktur Bidang 1, 2, 3, dan 4. Tanpa mengurangi rasa hormat, mohon maaf tidak kami sebutkan satu persatu. Yang terhormat jajaran struktural lainnya di Politeknik Negeri Jakarta. Yang terhormat Bapak Ketua Jurusan Teknik Mesin, Bapak Dr. Engineering Insinyur Muslimin STMT WE. Yang terhormat Ketua Jurusan Teknik Sipil Ibu Isti. Dan yang terhormat kepada seluruh struktural dan dosen di jurusan Teknik Mesin. Yang terhormat kepada seluruh direktur dan jajaran dari Politeknik Mitra RESD, baik dari Politeknik Negeri Ujung Pandang, Politeknik Negeri Bali, Politeknik Negeri Manado, dan PMCEKUA Akamigas. Dan yang kami hormati, leader dari GFA Konsultan Project, Bapak Martin Stotel beserta jajarannya, dan especially for the Mr. Thomas Gross. Hadirin sekalian, RESD program merupakan program yang lahir dari kerjasama antara government to government, antara pemerintah Indonesia dan pemerintah Swiss. Dalam pelaksanaan program ini adalah tujuannya untuk mempersiapkan dan mengembangkan sumber daya manusia di bidang energi terbarukan, khususnya energi surya dan energi hidro. Dalam pelaksanaannya, program ini dibagi beberapa komponen, salah satunya adalah komponen pendidikan formal, yaitu yang disebut dengan program spesialisasi 1 tahun energi terbarukan yang dilaksanakan di 5 politeknik, yaitu kita sendiri Politeknik Negeri Jakarta, Politeknik Negeri Ujung Pandang, Politeknik Negeri Manado, Politeknik Negeri Bali, dan PMCEKUA Akamigas. Dan saat ini adalah sudah memasuki angkatan ketiga. Dalam pelaksanaan pendidikan formal ini, setiap semester 10% dari perkuliahan itu akan diisi oleh expert di bidangnya, baik di bidang hidro maupun di bidang energi surya. Dan pada saat ini kita berkesempatan mendapatkan wawasan dari expert di bidang hidro, yaitu dari Mr. Thomas Gross langsung dari Switzerland. Tepuk tangan dulu untuk Mr. Thomas Gross. Tidak lupa kami mengucapkan terima kasih kepada semua stakeholder yang terlibat dalam acara pada hari ini. Semoga menjadi ladang amal ibadah untuk kita semua dan acara kita berjalan dengan lancar. Kami juga memohon maaf apabila ada kekurangan dan kesalahan dalam pelaksanaan kegiatan pada hari ini. Semoga kegiatan hari ini menjadi ilmu yang bermanfaat untuk kita semua, khususnya adalah untuk alma mater kita tercinta, Politeknik Negeri Jakarta semakin terkenal di kancah internasional demi mewujudkan visi PNJ menjadi Politeknik bertaraf internasional untuk mendukung daya saing bangsa. Terima kasih. Billahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Yulima Vendro, for the word. Moving on, let us listen to the speech from the head of Mechanical Engineering of Politeknik Negeri Jakarta. We kindly invite Mr. Muslimin to the stage.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera. Good morning. Izin ya, saya di sini mungkin akan memperkenalkan tentang program jurusan yang terkait dengan RSD ini ya, melengkapi tadi yang disampaikan oleh Pak Vendro. Kepada yang terhormat Bapak Direktur Politeknik Negeri Jakarta, Bapak Dr. Tamu SE MM. Kemudian yang hadir di sini ada Bu Wadir 4, Bu Rika. Kemudian ada Ibu Kajur ya dari Teknik Sipil, Bu Isti, alhamdulillah sudah hadir. Kemudian dari GFA Swiss, GFA ya yang melaksanakan kerjasama ini ya, yang mengoperate itu di sini sudah hadir Pak Bahtiar. Kemudian ada Mbak Dian, kemudian juga ada Mbak Devi ya di sini. Kemudian kepada yang terhormat Bapak Ibu dosen ya dan struktural jurusan yang tanpa mengurangi rasa hormat tidak saya sebutkan satu persatu, dan juga mungkin semua jajaran ya di PNJ juga yang tanpa mengurangi rasa hormat tidak saya sebutkan satu persatu. Kemudian terkhusus bagi mahasiswa ya yang sudah hadir di aula atau auditorium perpustakaan Politeknik Negeri Jakarta, juga kami ingin menyapa ya dari 5 politeknik ya, yang sudah hadir online ya di sini. Ada dari Politeknik Negeri Bali ya, ada Politeknik Negeri Manado, kemudian Politeknik Negeri Ujung Pandang, Politeknik Energi dan Mineral, PEM ya, Akamigas, kemudian dari Politeknik Negeri Jakarta. Nah, informasi dari Pak Bahtiar, tadi ada tambahan 5 politeknik lagi ya yang sudah bergabung, yaitu adalah Politeknik Sriwijaya, Negeri Sriwijaya ya, kemudian Politeknik PENS, kemudian Polman Bandung, kemudian Politeknik Energi dan Pertambangan Bandung, kemudian satu lagi adalah Politeknik Negeri Samarinda ya. Dan ini pun sudah dilakukan TOT ya. Jadi untuk dosen-dosennya itu dilaksanakan training of trainer yang sudah berjalan sejak tahun 2021 gitu ya. Jadi sudah lama programnya, dan sekarang di kita ini adalah sudah 3 angkatan. Ya, sudah 3 angkatan. Jadi program khusus 1 tahun ya. Nah, kita inputnya untuk saat ini dari D3. Ya, D3 Teknik Mesin, semua jurusan, semua prodi ya. Kemudian D3 Teknik Sipil, semua prodi. Kemudian D3 Teknik Elektro, semua prodi. Jadi kami menerima dari 3 jurusan ini ya. Kenapa? Karena memang itu akan berkorelasi, gitu ya. Dan untuk saat ini kita masih fokusnya di di pengembangan energi terbarukan ya, tapi mengkonversi dari energi fosil ke energi terbarukan. Ya sebenarnya ada dua ya, jadi ada efisiensi energi dan konversi energi, gitu ya. Nah yang konversi energi ini kita mengkhususkan di dua bidang, yaitu PLTS dan satu lagi adalah PLTMH. Jadi baru dua, insya Allah nanti ke depan bertambah ya Bapak Tiar ya. Jadi bukan hanya dua, tapi kita akan bertambah dengan energi-energi lainnya ya, yang terbarukan. Nah ini kenapa sebenarnya dalam mendukung zero emission. Ya zero emission karena Indonesia sudah menandatangani ya di tahun 2060. Ya jadi tahun 2060 kita sudah tidak menggunakan bahan bakar yang menghasilkan emisi yang besar, gitu ya. Dan ini adalah kerjasamanya tadi sudah disebutkan ya sama Pak Vendro, adalah G2G. Jadi government to government antara pemerintah Indonesia sama pemerintah Swiss. Ya. Baik. Alhamdulillah ya, dan alumninya juga sudah berkiprah di berbagai macam sektor ya, energi baru dan terbarukan ya, dan juga ya karena sekarang masih belum populer ya, masih belum ya, kita berkewajiban untuk terus mengkampanyekan untuk energi baru dan terbarukan ini. Jadi sebagian alumninya bekerja masih di bidang yang tidak relevan ya masih ya, tapi ya sebagian besar sudah bekerja sesuai dengan bidang energi terbarukan. Baik, mungkin itu sambutan dari saya sebagai ketua jurusan ya. Insya Allah jurusan teknik mesin sebagai pengelola ya kerjasama program Renewable Energy Skill Development ini tetap berkomitmen sesuai dengan arahan pimpinan ya, menjalankan kerjasama ini sebaik-baiknya, termasuk dalam melaksanakan kegiatan ini ya, kegiatan hari ini, yaitu guest lecture series RSD program ya, dengan tema Design and Maintenance of Micro Hydropower Plant. Jadi selain konversi energi ya, prodi lain pun akan berkorelasi. Kenapa? Karena desainnya ya ada di bidang manufaktur, misalnya gitu ya. Perawatannya ada di bidang perawatan gitu ya. Pembangkitannya ada di pembangkit dan seterusnya. Jadi tidak tidak karena saya mesin tidak bersesuai. Enggak ya, ini semuanya melibatkan banyak prodi, begitu ya. Dan ini tadi udah disebutkan ya sekitar 10%. Jadi kalau di rata-rata ya, baik expert dari Swiss atau dari luar negeri lainnya, dan ekspor dari luar negeri kalau di rata-rata ya untuk 5 politeknik ini sudah dilaksanakan rata-rata sebulan sekali ya Pak Batiar. Betul Pak Batiar ya. Jadi sebulan sekali dilaksanakan kuliah umum dan guest lecture. Ya mudah-mudahan pada hari ini kita bisa mendapatkan sharing ya dari expert Mr. Thomas Gross, yang juga beliau ini adalah sebagai trainernya dari training of trainer untuk dosen-dosen yang mengajar di bidang renewable energy, gitu ya. Demikian sambutan dari saya, mudah-mudahan nanti bisa bermanfaat. Silakan dimanfaatkan ya kesempatan ini untuk bisa menggali lebih jauh, bisa menggali pengalamannya ya dalam mengembangkan microhydro, karena beliau ini bidangnya adalah microhydro power plant dan sudah banyak membangun ya microhydro ini di berbagai macam negara. Demikian sambutan dari saya, mudah-mudahan bisa bermanfaat ya pertemuan hari ini. Kurang lebihnya mohon maaf. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera. Good morning.
Thank you, Mr. Muslimin, for your speech. Now, moving on to the next agenda, we will listen to a speech delivered by the Formal Education Manager of GFA Consultant RESD, Mr. Bakhtiar Salam. We kindly invite Mr. Bakhtiar to the stage.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, selamat pagi untuk Bapak Ibu semuanya. Hadirin yang kami hormati, sebelumnya kami hormati Bapak Samsul Rizal selaku Direktur Politeknik Negeri PNJ yang telah memberikan kesempatan luar biasa. Ini luar biasa, Pak. Jadi sebelumnya kami juga mengadakan di PEM Cepu, tapi dengan NRI Pertamina juga seperti ini. Jadi ini saya ucapkan terima kasih lagi-lagi Pak Prof. Pak Samsul Rizal, Pak Dr. Samsul Rizal, dan rekan-rekan Politeknik Negeri Jakarta, Politeknik Negeri Jakarta, di antara di sini ada Pak Dr. Muslimin selaku Ketua Jurusan Mesin, dan yang kami hormati juga dengan rekan-rekan ada Pak Vendro, rekan-rekan Prodi penyelenggara, yang sini saya familiar banget, ada Pak Cecep, ada senior kita Pak Janus, yang sebelumnya sudah mengikuti serius TOT untuk kegiatan TOT juga bersama dengan Thomas. Dan yang kami muliakan rekan-rekan dari GEVA Consulting Group, di sini ada Mbak Dian, terima kasih Mbak Dian atas kehadirannya. Harapannya nanti berikan speak juga, sehingga bisa berjalan lagi kegiatan lebih bagus lagi. Dan juga ada teman-teman kita, ada Pak Devi di sini selaku tim yang kebetulan kami hire dari Politeknik Negeri Jakarta untuk menjadi tim kami di kantor kami di GEVA Consulting di Jakarta. Mudah-mudahan lebih lanjut acara ini bisa berjalan terus karena sesuai dengan asta cita dari Presiden kita yang baru. Sebelumnya ada nawacita dari Pak Prabowo bahwasanya kita mendorong kemandirian energi, dan yang nomor 4 juga salah satunya untuk meningkatkan SDM di bidang energi teknologi sehingga kita setara untuk mendorong target sesuai dengan Pak Muslimin tadi ceritakan, perlu peningkatan transisi energi di tahun 2026. Artinya kebutuhan sumber daya manusia di bidang energi sangat dibutuhkan. Ini sangat relevan sekali. Silakan di insight dari Mr. Thomas. Welcome Pak Thomas. Sorry, I'm in bahasa. Bidang desain dan maintenance hydro, terutama di mikro hydro bisa dikembangkan lebih lanjut lagi, dan peningkatan ilmu ini bisa dikembangkan selanjutnya untuk rekan-rekan mahasiswa bisa diimplementasikan di dunia pekerjaan nanti. Dari saya tidak lebih, mohon maaf jika ada salah kata. Semoga acara bisa berjalan langsung, dan I would like to say hello for Politeknik. Di sini ada 4 politeknik yang hadir di Zoom meeting. Ada Politeknik Negeri Bali, Politeknik Negeri Manado, Politeknik Negeri Ujung Pandang, PEM Agam Migas Cepu. Jadi saya cek tadi sudah Zoom meeting. Saya ingin say hello, mudah-mudahan mereka akan berikan juga pertanyaan, terutama mungkin Politeknik Ujung Pandang kadang sangat aktif sekali, ataupun Politeknik Negeri Bali bisa memberikan pertanyaan-pertanyaan langsung ke Mr. Thomas saat kuliah tamu. Dari saya sekian, Assalamualaikum warahmatullahi wabarakatuh, salam sejahtera, Om Swastiastu.
Thank you, Mr. Bakriar, for your speech. Next, we're pleased to invite the Formal Education Manager, Communication of GFA Consultant RESD, Mrs. Dian Elvira Rosa, to deliver her speech. Please welcome Mrs. Dian to the stage.
Yang terhormat Bapak Dr. Syamsul Rizal, SEMM, selaku Direktur Politeknik Negeri Jakarta. Yang terhormat Bapak Ibu Wakil Direktur dan Ketua Jurusan. Yang terhormat Bapak Thomas Gross, sebagai narasumber kita pada pagi hari ini. Serta hadirin sekalian, para dosen dan mahasiswa Politeknik Negeri Jakarta, dan juga para mahasiswa dan rekan-rekan yang bergabung secara daring lewat Zoom ya. Jadi tadi ada beberapa politeknik yang disebutkan, ada dari Cepu, dari Bali, dari PMK Migas, dan juga dari Ujung Pandang. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Bapak Ibu, pada pagi hari ini merupakan momen yang sangat baik bagi kita semua, karena kita berkesempatan untuk menyambut seorang pakar dan praktisi industri yang terkemuka di bidang energi terbarukan, khususnya tenaga air, jauh-jauh datang dari Swiss ya, yaitu Bapak Thomas Gross. Welcome Thomas, hope you're not having a jet lag. That's good. Kehadiran Bapak Thomas pada pagi hari ini merupakan wujud nyata dari kerjasama yang sangat baik yang sudah terjalin selama 4 tahun terakhir antara Project Renewable Energy Skills Development atau RESD dengan Politeknik Negeri Jakarta ya. Jadi dari tahun 2021 hingga sekarang. Project Renewable Energy Skills Development merupakan proyek kerjasama yang didukung oleh pemerintah Swiss, Swiss State Secretariat for Economic Affairs (SECO) dan beberapa pemerintah dan beberapa kementerian di pemerintah Indonesia, antara lain Kemdikti yang mana melibatkan Politeknik Negeri di bawah Kemdikti, juga ESDM serta Kemnaker. Sebelumnya saya menyampaikan permohonan maaf dari Bapak Martin Stotle selaku pimpinan proyek RESD. Beliau tidak bisa hadir secara langsung pada pagi hari ini karena menghadiri acara di Bappenas untuk peluncuran program kerjasama Swiss dan Indonesia selama 4 tahun ke depan. Jadi program kerjasama dukungan dari Swiss untuk Indonesia itu akan terus berlanjut selama 4 tahun ke depan. Kami dari Proyek RESD itu sangat mengapresiasi kerjasama yang sangat baik antara RESD dan Politeknik Negeri Jakarta. Dari tracer study yang kami lakukan terhadap lulusan RESD dari Politeknik Negeri Jakarta, itu sudah banyak para lulusan yang bekerja di industri energi terbarukan maupun beralih ke industri energi terbarukan setelah mendapatkan pendidikan spesialisasi selama 1 tahun di PNJ. Dan seperti yang disampaikan oleh Pak Bahtiar tadi, junior expert di tim proyek RESD pun saat ini adalah lulusan dari Politeknik Negeri Jakarta. Itu Mbak Devi Monica ya, luar biasa. Ya. Ya, artinya lulusan dari PNJ itu bagus, dikenal bagus, jadi harus di-maintain ya. Kami percaya bahwa untuk meningkatkan kualitas pendidikan vokasi itu perlu selalu menjembatani kesenjangan antara dunia pendidikan dan dunia industri. Dan kuliah tamu pada pagi hari ini merupakan langkah yang sangat bagus dalam proses tersebut. Karena di sini mahasiswa bisa berinteraksi secara langsung dengan pakar ahli industri ya, yang memiliki pengetahuan bukan saja tentang konteks Indonesia, karena beliau Pak Thomas Gross ini sudah cukup sering ya datang ke Indonesia, namun juga pengalaman-pengalaman internasional yang sangat kaya. Kita mungkin sudah mengetahui bahwa energi terbarukan secara khusus pembangkit listrik tenaga air itu memiliki peran yang sangat penting untuk terus mengupayakan pemanfaatan energi yang lebih bersih dan berkelanjutan. Dan dalam hal ini pembangkit listrik tenaga air itu cukup unik karena dia bisa dikembangkan bukan saja dalam skala yang besar tapi juga secara skala kecil, mikrohidro, yang dapat dikelola bahkan oleh kelompok masyarakat yang kecil. Dan mungkin kita juga sudah mengetahui bahwa Swiss dengan segala sumber daya air yang sangat banyak itu memiliki pengalaman yang kuat dan juga yang sangat bagus dalam hal pengelolaan pembangkit listrik tenaga air secara efisien dan berkelanjutan. Nah, di sini Bapak Thomas Gross adalah expert trainer dari RESD yang memang fokus pada bidang pembangkit listrik tenaga air, dan beliau adalah praktisi sebagai pemilik perusahaan di Swiss ya, khusus untuk pembangkit listrik tenaga air, dan juga beliau adalah dosen ya, dosen di Zurich University of Applied Sciences. Dan beliau memang memiliki pengalaman cukup banyak juga dari sisi konsultasi ya, memberikan jasa konsultan di berbagai belahan dunia. Jadi saya berharap agar kuliah tamu pada hari ini bisa berjalan dengan lancar. Untuk teman-teman mahasiswa, apabila ada pertanyaan silakan ditanyakan, bukan saja mahasiswa yang hadir di PNJ tapi juga yang secara daring lewat Zoom ya. Jangan sungkan-sungkan untuk menggali ilmu dari Bapak Thomas Gross. Kalau misalnya mau diajak pakai bahasa Indonesia pun nggak masalah, supaya beliau juga belajar ya dikit-dikit. Nah, kita ada di sini interpreter Mbak Intan, di mana Mbak Intan. Nah, nanti kalau misalnya ada pertanyaan dalam bahasa Indonesia pun itu bisa diajukan kepada Bapak Thomas Gross. Akhir kata, saya mengucapkan terima kasih banyak kepada Politeknik Negeri Jakarta, khususnya kepada Prodi Ariesdi ya, Pak Vendro, Pak Muslimin, atas persiapan yang sangat luar biasa dan semoga acara kita pada hari ini membawa banyak manfaat bagi kita semua. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mrs. Dian, for your speech. Ladies and gentlemen, we now invite the Director of Polytechnic Negeri Jakarta to deliver the opening remarks and officially open today's event. Please welcome Mr. Syamsu Rizal to the stage.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning everybody. Yang saya hormati Leader GVA Konsultan Project RSD, Mr. Martin Stoll, yang kebetulan hari ini tidak hadir dan diwakili oleh Pak Bahtiar dan Bu Dian. Terima kasih Bu Dian. Direktur Politeknik jajaran yang bekerja sama dengan RSD, Politeknik Ujung Pandang, Politeknik Bali, Politeknik Negeri Jakarta, dan Politeknik Negeri Manado, dan PEM Akamigas Cepu yang bergabung melalui media online. Yang saya hormati Ketua Jurusan Teknik Mesin yang memfasilitasi dan menginisiasi untuk kegiatan pagi hari ini, bekerja sama dengan RSD yang memang menugaskan kita untuk ada kuliah tamu pada pagi hari ini. Terima kasih kepada Mr. Thomas Gross yang sudah berkenan hadir di Politeknik Negeri Jakarta. Yang saya hormati juga ada Bu Isti, Ketua Jurusan Teknik Sipil, yang ikut support kegiatan pagi hari ini. Tentu yang saya banggakan adalah juga dosen-dosen dari teman-teman teknik mesin yang support, pertama Ketua Pelaksana, Mas Pedro, dan tentu adik-adik mahasiswa yang berbahagia pada pagi hari ini. Kita mendapat kesempatan yang baik dan langka. Pada pagi hari ini kita ada kuliah tamu, guest lecture yang akan diisi oleh Thomas Gross, tadi sudah disampaikan. Beliau sangat berpengalaman di bidang energi untuk pembangkit tenaga air. Nah, galilah ilmu ini yang sebanyak-banyaknya. Nanti silakan bertanya, boleh menggunakan bahasa Indonesia, tadi informasinya begitu. Sehingga nanti tadi digambarkan kenapa pemerintah Indonesia bekerja sama dengan pemerintah Swiss. Karena pemerintah Swiss adalah sangat konsen bagaimana untuk energi terbarukan ini untuk tahun 2060. Mereka sudah berpikir jauh ke depan. Tentu 2060, saya tanya nih adik-adik mahasiswa, kira-kira Anda berada di mana nanti? Atau berumur berapa Anda di 2060 itu? Kalau dilihat dari sisi umur, saya tidak akan cukup lagi. Dosen-dosen juga mungkin tidak akan sampai pada usia tahun 2060. Tapi adik-adik mahasiswa yang saat ini berumur 20 tahun atau 21 tahun, ditambah dengan 35 tahun akan datang, Anda adalah penentu-penentu kebijakan negara ini. Anda adalah orang-orang yang akan menentukan kemana negara kita ini berada. Atau energi-energi mana yang akan bisa kita gunakan. Tentu kita juga sadar bahwa energi yang tersedia di negara kita, walaupun disebut Indonesia negara yang kaya raya, tapi kenyataannya yang dinikmati hanya segelintir orang. Nah, tentu Anda di 2060, Anda yang akan menentukan di mana masa depan negara ini. Tadi kalau Anda ingat bagaimana lagu Indonesia Raya, bagaimana himne Politeknik Negeri Jakarta, tentu terlihat kita adalah mendukung dan menjunjung tinggi bagaimana kita menjadi Indonesia maju. Anda adalah menjadi produk-produk unggul. Nah, tentu saya sekali lagi mengucapkan terima kasih kepada teman-teman di Teknik Energi atau di jurusan Teknik Mesin menginisiasi ini. Dan pada hari ini cukup luar biasa, memang yang hadir tidak hanya di sini, juga ada yang hadir melalui via Zoom. Nanti silahkan didengar secara baik dan cari informasi sebanyak mungkin. Karena tadi informasi dari Pak Batir dan Mbak Dian bahwa Thomas Geran ini adalah salah satu yang sudah banyak menjadi konsultan dan juga pelaku bisnis yang di negara-negara lain. Nah, tentu Indonesia diharapkan yang memang sumbernya luar biasa Indonesia ini. Jadi saya berharap adik-adik mahasiswa lah 10-15 tahun ke depan Anda yang menjadi pelakunya. Nah, saya juga di sini juga berdasarkan laporan bahwa Politeknik Negeri Jakarta ini bekerja sama dengan RSD yang ada di Indonesia. Kita sudah bekerja sama dari tahun 2021 dan jumlah mahasiswa yang sudah dihasilkan itu adalah berjumlah 130 mahasiswa. Dan mahasiswa ini juga berasal yang ada di PNJ, ada yang dari BUMN, yang lanjut studinya ke RSD, ada juga yang dari PLN, ada juga yang dari Pertamina, ada juga yang PNS. Jadi tidak murni hanya lulusan Politeknik yang melanjutkannya. Tapi ini Anda menjadi tahu, tadi apa yang diinformasikan oleh Mbak Dian, kan kita panggil Ibu, kayaknya masih muda ya Mbak Dian ya. Artinya apa? Itu sangat detail dan lengkap. Ini adalah merupakan prospek yang baik. Tadi baik buat jurusan yang disampaikan oleh Pak Muslim tadi, teknik elektro, apakah itu teknik mesin, apakah itu juga teknik sipil tadi juga dikatakan. Jadi ini peluang. Bahwa peluang ini tidak akan datang sekali, dua kali. Peluang itu hanya datang sekali, jadi Anda putuskan dan Anda ambil hikmahnya. Sehingga Anda setelah ini yang D3 tadi boleh silakan melanjutkan untuk yang di RSD. PNJ juga telah mengirimkan sebanyak 15 orang yang dosen kita yang sudah TOT dan mudah-mudahan tahun ini juga akan ada di Manado. Dan tadi yang saya tanyakan kita juga mengirim Pak yang kesediaan dari Pak Gun-Gun ya yang siap berangkat dan Pak Adi. Tadi Pak Adi ada saya lihat. Karena kemarin informasinya belum daftar juga, saya bilang ternyata sudah ya. Ya, jadi saya juga agak mendorong juga. Tentu program ini sangat bermanfaat untuk Politeknik Negeri Jakarta. Hal ini tentu dirasakan langsung oleh mahasiswa dan juga oleh dosen. Nah, tadi dosen sudah TOT, tentu dengan TOT ini dia bisa, kalau industrinya ini tumbuh berkembang, ya dosen-dosen diharapkan menjadi pendamping. Kan begitu harapannya. Dan mahasiswa adalah menjadi pelakunya. Nah ini harapannya. Tentu ya dosen ini agar juga mengembangkan riset-risetnya dia. Jadi dosen itu tidak hanya selalu ngajar aja di kampus. Seperti tadi saya gambarkan digambarkan Pak Beta, Thomas Gross, adalah juga dosen tapi juga pelaku bisnis. Itu yang ideal. Seorang dosen itu dia juga pelaku bisnis dan juga adalah mentransfer knowledge-nya kepada mahasiswa. Jadi kembangkanlah, ini kesempatan yang terbaik buat kita. Jadi saya mengharapkan program ini juga menjadi salah satu program unggulan dari Politeknik Negeri Jakarta, sehingga dapat mencapai visi PNJ yang menjadi Politeknik unggul dan kita menuju bertaraf internasional. Insya kita juga ada 4 prodi kita yang sudah terakreditasi internasional, 2 dari jurusan teknik sipil, dan kemarin selamat juga untuk jurusan teknik elektro. 2. Jadi tahun ini kalau memang ada dari jurusan teknik mesin yang bisa terakreditasi internasional, kita dorong. Mudah-mudahan nanti tahun ini kita juga dapat kuota 1 atau 2 lagi prodi yang bisa kita akreditasikan internasional. Ya, puji alhamdulillah kita ucapkan kepada jurusan teknik elektro yang kemarin ada syukuran. Ya, saya juga ikut hadir. Tentu ini tidak mudah. perjuangan ini. Mungkin Bu Isti juga merasakan betul bagaimana di teknik sipil di 2024 dan 2025 ini kita beruntung 2 prodi di PNJ terakreditasi internasional. Secara IKU kita sudah memenuhi standar. Artinya politeknik itu minimal 10% dari jumlah prodinya. Jadi itu sudah tercapai di kita dan tambah 2 tahun ini kita naik lagi. Jadi ini yang bisa saya sampaikan dengan ini langsung dibuka ya Pak? Atau saya buka apa enggak? Langsung ya. Jadi kasih pertanyaan itu takutnya dengan mengucapkan Bismillahirrahmanirrahim, kegiatan Gesdecer RSD program secara resmi dibuka. Terima kasih. Akhir kata, Assalamualaikum warahmatullahi wabarakatuh.
Mr. Shamsurizal, please remain on the stage. Thank you, Mr. Shamsurizal. And with that, the guest lecture series of the Renewable Energy Skill Development is now officially open. Please give a big round of applause. Next, we would like to present a gesture of appreciation from PNJ to Mr. Thomas Gross. To mark this special occasion, we kindly invite Mr. Thomas Gross to the stage. Please give a big round of applause as we carry out this meaningful exchange. And next, we will have a group photo session with all participants. Mr. Shamsurizal and Mr. Thomas, please come down to join us for the documentation. And for all participants, please kindly stand up. Please kindly look towards the camera. The count on me. 1, 2, 3. Oh. Okay, 1, 2, 3. Show us the spirit of PNJ pose. 1, 2, 3. Okay, thank you. You may return to your seats. Ladies and gentlemen, moving on to the main agenda, now it is my honor to hand over the stage to our esteemed moderator, who will guide us through the program. Please welcome Mr. Pribadi Mumpuni Adi as a lecturer in the Mechanical Engineering Department, and please give a big round of applause.
Okay, good morning everyone. So, saya bicara bahasa Indonesia dulu ya. Oke, jadi kita akan mulai untuk guest lecture-nya. Pertama-tama, tolong yang di belakang bisa ngisi yang depan dulu ya. Ini masih ada 2 baris kosong di sini nih. Ini tolong diisi dulu ya. Jadi diatur dulu yang belakang-belakang, yang mungkin di sebelah kiri ya atau di kanan saya bisa pindah terlebih dahulu ya. Jadi tolong diisi dulu yang bagian depan, bisa maju ya. Karena masih ada yang kosong kursinya. Sehingga yang di bagian kiri bisa ikut memenuhi yang ke tengah ya. Silakan diisi dulu, diatur lagi posisinya. Baik, kepada yang terhormat Bapak Direktur PNJ, Pak Samsul Rizal, serta jajarannya, dan juga dari tim RSD beserta jajarannya, dan juga para tamu undangan yang hadir melalui Zoom, selamat datang, dan juga pada adik-adik mahasiswa. Oke, now let's begin our guest lecture. So, lecture ini ya nanti akan disampaikan dalam bahasa Inggris ya. Jadi memang nanti dalam bahasa Inggris ini tidak ada translate-nya. Tetapi kalau nanti kalian mau bertanya nanti Mr. Thomas itu akan mempersilahkan. Jadi kita kurang lebih akan di sini selama 2 jam ya. Kurang lebih akan selama 2 jam. Jadi 2 jam itu nanti kalau ada waktu itu langsung di sesi ada tanya jawabnya. Jadi tidak tanya jawab itu tidak ditaruh di belakang. Jadi nanti mungkin Mr. Thomas akan silakan kalian jika ada pertanyaan, nanti silakan untuk bertanya ya. Jadi biar kalian tidak terlewat ya apa yang mau ditanyakan. Jadi tidak perlu menunggu di akhir acara untuk bertanya. Oke. So now I will invite Mr. Thomas Gross to the stage. And before we start the lecture, so I will introduce him first. So I already have the CV, so I will introduce you in Indonesia. Maybe they will understand more. Oke, so Mr. Thomas Gross is a chartered engineer. Jadi kalau kalian baca ya, itu chartered engineer. Nah ini mungkin pengetahuan baru ya. Charter itu bukan kalian seperti charter pesawat, bukan ya. Jadi bukan engineer sewaan, bukan. Itu artinya adalah engineer profesional. Nah gitu ya. Jadi insinyur profesional yang sudah tersertifikasi. Gitu ya. Jadi charter engineer itu seperti kalau di Indonesia itu ada yang namanya PII ya. Nah, PII Satuan Insinyur Indonesia. Nah, itu kalau kalian PII kemudian dapat insinyur ya kalian bisa disebut sebagai chartered engineer. Nah, gitu ya. Nah, beliau ini adalah seorang chartered engineer dan bidangnya adalah di bidang geomatics ya, from ETH Zurich. Nah, kemudian beliau juga saat ini memiliki atau founding sebuah perusahaan namanya Hycon. Ini di bidang energi dan infrastruktur ya. Nah kemudian beliau juga banyak proyek ya, proyek-proyeknya di bidang hydropower project. Dan saat ini beliau adalah pengajar di ZHAW Zurich University of Applied Science. So so for now I already introduce you. Please now the stage is yours. So please. And if you you can, I think there will be a slide here for your slide, so you can there. Yes. They will ada. This is the microphone. Gak ada slide. So they will directly if you need to say change slide, just say next. Okay. They will directly change. Yeah. Do you need this one? Yeah. Okay. First one? Yeah, please next one. Oh, the first one. Kembali ke slide awal coba.
Okay, let's start here. Okay, let's start on this slide. Good morning, ladies and gentlemen. It is a big pleasure for me to be here at the Polytechnic Negeri Jakarta. It's great to be back here. It's the 3rd time and now able to provide this guest lecture on design and operation of small hydropower. First of all, many thanks for the warm welcome and the pleasant introduction. Just at the beginning, a few slides so you have an idea of what I'm doing. I'm now for more than 20 years or almost 20 years in the field of renewable energy. We provide consultancy services, as you see on my slide back, so it's not only engineering, but we really care mainly on the people in rural areas when we provide access to energy and other infrastructure and we try to have a holistic approach. Next slide. Yeah. And as you can see, it's not only Indonesia. I've come to Indonesia the first time in 2006. And ever since I've been working here, I've been working in Central Asia, but Africa as well. So this just shall give you an idea of places I've been working and delivering services to enable people, mainly in the rural area, to have access to energy and to generate a decent income. Next slide. So in the next few minutes, ladies and gentlemen, if you allow, first we should talk on water, because if we want to have a hydropower plant, then we need water. And in many areas, water is not available in an unlimited manner. So we need to talk about the water, energy, and food nexus. This is very important to understand when we go and implement hydropower plants. Next slide. So this water, energy, and food nexus is literally this kind of magic triangle. And I think this is important to understand. If you imagine if we have a riverine, a water flow, this water at any given point, we can use, for example, for irrigation to create food. But if we use it for irrigation and we divert it from the river into our fields, then it's no longer available for a hydropower plant. In the opposite, if we produce food, if we produce vegetables, we need to process it, we need to cool it. So we need electricity for this, meaning that we need to have water for our hydropower plant. And therefore we cannot use it for irrigation anymore at the given spot. So this needs to be considered very carefully when we plan our projects. And if we do an intervention in a region, so that we always have this kind of magic triangle between water, energy, and food. Next slide. In times as we have this year, and with a lot of turmoil and uncertainty, also from what was considered one probably of our close friends in the US, but still you see, the US Department of Energy already published these key statements 10 years ago, and they are still valid and they are still unchanged also from the US Department of Energy. So we need to understand that, as I explained on the previous slide, energy and water, they are interdependent. There is no disconnection between water and energy, be it for hydropower. But if we think of large power plants, if you have a coal-fired plant or an oil power plant, or even a nuclear power plant, you need water for cooling. So without water, there is no energy. What also is important to remember, that fresh water is not available in an infinite manner. So fresh water is somehow limited, and there will be a change in the future. We cannot assume that it is as it was in the past. With all the arising problems we have, be it climate change, be it a higher consumption of water, we need to have an integrated approach to manage our water systems. Next slide. These are the so-called Dublin principles for integrated water resource management. And this is important to understand. As said, we need to see our water resources in a holistic manner. And as I already said, one of the principles is that fresh water, non-salted, pure water, clean water, this is a finite resource, is not available in unlimited amounts. So we need to take care of it. When we want to do water management, and I think you also have a tradition here in Indonesia on water management, we need to have a participatory approach. Specifically, when we come to rural areas, we need to include the communities in water management, and we cannot just provide a top-down solution. In many countries, globally speaking, women will play a key role in water management. You might have seen it, it might be here in Indonesia, but it's definitely in a lot of other countries, that when it comes to water, be it for drinking water, collecting for the households, but as well for farming, the women play a crucial role. And therefore, when we say we need an integrated approach on water resource management, and we need to have participation from the community, we need to include all members of the community, specifically the women. And the last one, that water has an economic value. Please don't get me wrong, it's not the idea that we're going to do a big business with drinking water, selling water in bottles, that's not meant. But as the availability of water is limited, we need to put a price tag on the water, because if you have limited resources, but you provide it for free, people will not take care of it. So the people need to understand that access to water has a value, that access to water or the availability for water cannot be just for free, and you can just use it without thinking at it. Next slide. So talking of water, I think this water cycle is well known to you. You see it here on a global level. And we somehow need to understand that whatever water we have in the ocean will somehow evaporate and come down as rain again. So, and you see the quantities here on a global level that might vary over time, but in general, that's applicable. Next slide. Yeah, and this is very interesting, and you can imagine where is Indonesia? Indonesia right now here, Jakarta is about 6 degrees south. So and you know it very well, we're in an area where you have probably more rain than evaporation. If we go further down south, we come into an area where we have more evaporation than just rain. And this is on a global level relevant to understand that we have areas where we have not so much rain, and therefore less water available, and other areas where we have more rain than evaporation. Next slide. Now, talking of climate change, and I just want to give you here an example from Switzerland, but to show you the relevance of climate change on river runoff, and therefore the consequences also for hydropower or hydroelectric production. What you see here are potential climate change scenarios on the temperature, depending on which model you take. And you see how the curves go up in relation to the CO2 emission equivalents. And you see the temperature change depending on the model. So from models of a increase of temperature of 1.5 degrees Celsius up to 4 degrees Celsius on a global level. These are the different climate change scenarios which we have. Next slide. And this is what happens with the river runoff. What you see here, you see the thick black line. This is what is a normal river runoff in Switzerland. And as you see, normally we have a low runoff in winter, January, February, and also to the end of the year. And we have a high runoff in summer. Now, what happens when climate change comes into play? And you see, we will need to assume a shift where we have much drier summers. So you see all the lines, they come down in the summertime. So we have drier summers and we have much more water in winter. Now, Switzerland has the challenge that we have cold winters and warm summers. So, for example, our farmers can only produce food in summertime There is no crops in winter. So we have only the period from March, April to October to harvest our crops. And you can imagine if we have much less water in summer, due to climate change, we have also an irrigation problem because the water is not there anymore. So this is a real impact of climate change on river runoff. And therefore, it is relevant to see again our water system, the ecosystem of our rivers in the context of climate change, and therefore to derive consequences also for hydropower production. Next slide. Yeah, these are just for your information. This is for different areas of Switzerland. Switzerland is much, much smaller than Indonesia. Huh? So you can pack whole Switzerland into Java Island and you wouldn't mention it. So, but anyway, what you see here, you see an increase in temperature overall. You see a reduction in precipitation, so we will have less rainfall but higher temperatures. And if we have rainfall, we will have more storm weather. So this seriously impacts a country like Switzerland. Next slide. And this is now the consequences for hydropower generation. As you see, we will have less water available in summer, so we can produce yet less hydroelectric power in summer because we have less water in the rivers. But we might have more water in the winter time in our rivers, which for us, and you see here, this is the energy statistics for Switzerland. Switzerland has about 2/3, 60% is hydropower, and 30% is nuclear power, meaning that we might produce a little bit more hydroelectric power in winter, but definitely less in summer. Next slide. Interesting, and I think this is also worth mentioning when I look on the transition to renewable energy, which is also one of the major goals for Indonesia. We always say that renewable energy, and I'm talking now mainly of solar and wind power, that they are fluctuating very much. So you never know, is there a lot of PV electricity, or is there a lot of wind, or is it there less? A German institute has made a long-term study, and what you see is that solar and wind, they're actually complementary. So normally if there is no sun, then there is wind, and if there is no wind, then there is sun. So if you look on a long-term average, you see that you have, with the combination of solar and wind, more or less a constant yield of renewable energy. Next slide. Now, this is probably more familiar to you. That's about the energy production in Indonesia, or the energy source, where we see that Indonesia still has a large potential for the transition into renewables. You rely on the resources you have, be it coal, be it oil, which are vastly available here in Indonesia, and therefore it was exploited and used for energy, which made sense at the time when the decision was taken. But we see also that we have the potential to shift into renewables. Next. When we look on the domestic level, now we're talking household level here in Indonesia. You see here as well that a lot of people in Indonesia, they still rely on bioenergy, for example, for cooking and heating. So there is still also a large gap in access to electricity for all applications within a household. And I think here we can also, by further expanding our electrical system with adding more hydropower, for example, to the Indonesian system, we still can here also transition in on household level when it comes to the energy consumption. Next slide. What is also interesting, on one hand, this is what I said, we still have a large potential for hydropower in Indonesia. That's what you see on the table on the right. There is still, in the major regions, still an untapped potential. On the other hand, hydropower is also a very cost-effective energy solution for Indonesia. As you see here, compared to other renewable energies, hydropower has one of the lower levelized costs of energy, and therefore you can, in a large scale, generate electricity at an affordable cost, then also for the consumers. Next. Now, is hydropower sustainable? Yes, in my opinion, yes. On one hand, if we use water in our hydropower system, not a single drop is lost. We don't pollute water in our hydropower system. We don't use it for anything else. We just transfer it to our system and we give it back to the river. On the other hand, as you see on the right-hand side of the slide, with hydropower, we can also be supportive of numerous sustainable development goals as formulated by the UN. As already indicated earlier, first of all, yes, with hydropower, we generate access to energy, but providing a reliable and cost-effective source of energy also enables an economic growth. And I think that's what we all strive for at the end. We are not going to produce power plants just for the sake of power plants, even though as engineers, we like to do good infrastructure. But at the end, whatever infrastructure we build, it must support our people and it must support an economic growth in our countries. As it helps further on transitioning to renewable energy, we definitely have a positive impact on climate change. We have a positive impact on life on land. And it can also has an impact on peace and conflict resolution, as we might have less dispute on other limited resources. Next slide. Next. Thanks. So how can we generate value with a hydropower plant? Let's assume we have somewhere in rural Indonesia a hydropower plant or a project for a small hydropower plant. How can we generate value? On one hand, and that's what you see in the red boxes, is during construction. When we build a hydropower plant, we need labor. We need people working there, and they do paid work. So we can generate already some jobs at the time of the construction. Further, we need to purchase equipment and materials. And let me admit that here in Indonesia, we have a very vibrant sector for renewable energy for hydropower plant. We have a lot of companies providing components for small hydropower plants, be it turbine manufacturers, be it electrical engineering companies, etc., who provide this equipment. So here we have already an industry in Indonesia which can provide the required components, and therefore by installing new hydropower plants, we can also benefit from our existing industry here without the need of importing goods or services from abroad. And let me have this word also to you here, dear audience, as you are here. You see, this is also your future. There are jobs available in the energy sector. And I think this is important also for you to know that as you are now investing your effort, your time here of getting graduated from PNG and all the other polytechnicums who do a fantastic job, I'm very much convinced that there is an energy sector in Indonesia who is looking for well-educated young people, and I'm pretty sure there will be jobs for many of you. On the other hand, and we go to the blue boxes, you see by having a hydropower plant, for example, available in our area, and therefore access to energy, to electricity, we can go into value generation. So be it that we can have an enhanced agricultural value chain because we can process food, because we can store our food with a cold chain, we can create more value at the location. We can provide a reliable energy source also to social institutions, be it schools, be it hospitals, be it community centers, be it religious buildings, and therefore improve the overall livelihood of the people in that area. Next slide. So when we talk of productive end user, that's exactly the income generation. There are multiple options what we can do. Mainly connected to agriculture, that what happens in the rural area. And we can heavily increase the productivity of our people in the agricultural sector by having access to electricity in an affordable way to then increase the values of their product and not just selling the raw products from the field. Next slide. Saying this, we also need to consider when we plan our hydropower plant, what are the potential value chains? Where can we create new income generating activities? So we need to optimize also our hydropower plant production. At night time, we have a domestic use, which is probably not as high as during day. During day, we have the productive use. We have the value chains from agriculture. We have certain craftsmen. We have other activities, income-generating activities and businesses. But we really need to optimize our hydropower plant already at the design stage to optimize or even maximize this productive end use, which at the end is creating income. Next. So specific for farming, you see, I already explained it to you with renewable energy or hydropower in rural areas for farming. We can manage our waterways. So with a hydropower plant, we, for example, can also regulate certain flood situation and therefore protect our fields from flooding. We can use the energy for our agricultural value chain, and we have a reduction of greenhouse gas emissions. Next slide. Looking at, for example, Indonesia's agricultural products, you see, and probably we look on the right-hand side, because the left-hand side, more than half is palm oil, but you see the variety of agricultural products from Indonesia. Next slide. And this is very interesting, actually. This is the value chain from farming, and you see that with electricity, this green box here somewhere on the left-hand side, this is key to many applications in the agricultural value chain in rural areas here in Indonesia. Next slide. So here's some examples. Let me assume we have a horticultural business or a farmer here in Indonesia. So with access to electricity, he then can have a cold chain and preserve his products. So this increases the value of his products. He doesn't need to sell it immediately, but he really can adapt the sale of his products according to the demand side. When we look on the rice, also, instead of just selling the raw rice, we can process the rice from drying, milling, and packaging, and then sell the ready processed rice. And therefore, we have a higher value creation in the rural areas. Same is with sugarcane, where we don't need just sell the raw sugarcane to large companies, but we can generate income, additional income by processing it. Next slide. So this is kind of the core elements for productive end use. And this is very important because you see, when we plan a hydropower plant, we need acceptance from the people who live there. And generating acceptance is specifically then possible when we can convince the people that they will have an added value from the hydropower plant. And an added value in many cases is a higher income. And how can we create a higher income? We need to create access to electricity. That's clear, that's our purpose. But we need also to train the people on how to set up a business. It's very important. People need to understand how to do a business. And third, they need access to financing. Imagine if you want to start a business, you need somehow access to finance to kickstart your business. On the other hand, you see as well, for every kilowatt hour of electricity productively used, we can generate at least $1.5 of income. And if you imagine that electricity from hydropower here in Indonesia is somewhere around 10 US cents, or even a bit more or less, that doesn't matter. But if you can generate $1.5 out of every kilowatt hour, you see the margin you have for income generation by having access to renewable energy. Next slide. Here's some examples, just visually, of what is productive end use once you have access to electricity. Next slide. Here's some examples from evaluations I did. And you see, I gave you the figure of $1.5 US per kilowatt hour in some other projects. And you see the column to the right. The income generation can also be much higher, where we had proof of projects where the income generation was up to $3 or $4 per kilowatt hour, and therefore had a significant impact on the livelihood of the people. Next slide. Yeah, this is just the comparison of the GDP. Next. So let's have a few slides on the design. This was now the first introduction on understanding the context of access to water, using water for hydropower, and the impact on a community. In the next few minutes, I would like to talk a few words on a design approach, and then we will do a quick break and the Q&A session, the first one. Next slide. So this is the project life cycle. My dear fellow students, I know as engineers, we always strive for the moment when we can start off an infrastructure, the moment we press the button and the power plant or a machine starts to operate. That's the biggest thing for us as engineers. But if you remember one slide from my guest lecture here, please remember that a project continues further. We need to see the whole project life cycle. And one of the major issues what we have with failed energy projects is that people don't consider operation and maintenance as part of the life cycle. So as you see here, we normally start with the identification. This is more a theoretical exercise. We look on data, we look on maps, we do a desk study, and then we go to the field and we do a feasibility study. In many cases, you have somebody financing it, And therefore, the feasibility study is really the phase where at the end you decide, is it a go or is it a no-go? So here we really need to invest enough time and resources to have a quality data available for our decision making. Once we come to the conclusion that our project is feasible, we go into the detailed design and tender phase, where we do all the detailed design and we tender the contractors, so that we then can go into construction and commissioning, and last, the operation and maintenance, which is actually the most important and most underrated phase in the whole project cycle. Next slide. This is just for your information here, an idea of how much time it takes. And as you see, a small hydropower plant, normally we can realize within 2 years. If you look on large dams, large hydropower project, and you might have seen one or the other also in the media here in Indonesia, this normally takes much more time. And it's easily that it uses 10 years or more until a large hydropower plant becomes operational. Next. So what is our general design process? Are we now talking only on the design? First of all, we need to define the scope. What is the idea of our hydropower plant? And here in Indonesia, this is very relevant. Is it a small hydropower plant somewhere in rural areas, just for a village, no grid connection? Then we need to do it specifically for that area. Is it grid connection? Are we becoming an independent power producer? This is a different scope, probably a bit more challenging due to the current regulation here. You can become an independent power producer, but there are some hurdles to take. So this scope is to be defined. We need to have a clear picture on the economic situation. What are the potential tariffs? How much money can we create over the lifespan of a project? We need the technical design. I think this is clear, as we are all engineers. But then please look at the blue dot. That's the important one, the institutional setup. And that's where the sustainability is. A sustainable hydropower project is not coming just because we are good engineers and make a nice design. A sustainable hydropower project comes at the end from a durable institutional setup, so that if we have a hydropower plant, we have a committee taking care of its operation. We have people collecting tariffs. We have the consumers willing to pay tariffs for it. And then we have also the savings on a bank or whatever, so that we can invest in the future in rehabilitating and replacing equipment. So that's actually the key part. Next slide. Now, when we do the design, we have some dependencies, and some of you are, let's say, more the civil engineers, then you're probably more on the left-hand side. Topography, if you're surveying, what is our head, what are the geological features, etc. Maybe we have some hydrologists here, or people who are looking into hydrology to know how much water is available. This would fill another guest lecture with no problem. Then we have the detailed design in the middle, be it mechanical engineering, be it civil engineering, be it electrical engineering. So you see, we are really a power plant. A hydropower plant is really an interdisciplinary project where we need all faculties, civil, mechanical, and electrical engineering. As mentioned earlier, we shall not forget that there are also social impacts of a hydropower plant. So we even need people from social sciences to successfully implement a hydropower plant, because we need to have the community, we need to have an ownership within the community, we need to have a community to be able to pay for the tariffs. So you see, we have these socioeconomic factors which shall not be forget. Next. Yeah, when we talk on socioeconomic aspects, and this is important to understand specifically for us as engineers, that any hydropower plant, first and foremost, must be economically viable. That's sometimes our problem as engineers, that we do an excellent design and we are very convinced of our work, and then the finance people come and say that's a nice project, but it's not economically viable. And then we are very disappointed. So as engineers, we also need to think in economics. We need to have an economic viable project. Secondly, if we build a hydropower plant, that has an impact on the ecosystem where we build it. So it also needs to be socially accepted. Otherwise, we create tensions in a village. If people are unhappy with our project, we create tensions, we create conflicts, and this shall be avoided. And last but not least, we need to think of how do we manage our hydropower plant. It's the institutional setup. And if we have this triangle, these three aspects, then we have a sustainable approach. Next slide. Yeah. When later today we talk on the design, we normally talk on the supply side. So with an existing river, how much energy can we produce? But sometimes we also need to think on the demand side. So who are our customers? Who is there? Who is taking our electricity? Do we have the demand for the power plant which we plan? Or can we supply actually the demand? Is our power plant big enough? So you see here some aspects on the demand side analysis and some points to remember when you do an assessment in the field. So to find out how is the current consumption, what will be future consumptions, what's the ability and willingness to pay, etc., etc. Next slide. Now, probably more for our electrical engineering colleagues. When we do a hydropower plant, we automatically are generating a mini grid. As you see here, the example, and now this is an example for photovoltaic systems. There we have the choice on how we provide access to electricity with PV systems. As you see here on the left-hand side, you either can just install single rooftop systems, just providing electricity for the single household. We can connect different existing systems, or we build a power plant and feed it into a grid or even a national grid. For a hydropower plant, we cannot build a hydropower plant in every household, so we automatically have a mini grid, and therefore we need to have a proper mini grid design as well. Next slide. As mentioned, with the mini grids, we in addition have two options. Either we have an isolated grid, and there we need to make sure that our hydropower plant also has a black start capability so that it can start up without any external sources, or we are connected to the national grid and just feed into the grid, or probably also can provide a backup in case of a blackout. Next. So here's some key principles for off-grid electricity provision. Development cooperation, that's the first point. Development cooperation for a long time made a big error by fully financing investments in infrastructure without requiring any contribution from the recipients. So if we install a mini grid or a hydropower plant and it's fully financed by externals, this hydropower plant or mini grid will not have any value to the people benefiting from it. So we need to make sure that also the recipients or those, the consumers, need to make a contribution. Renewable energy technology needs to be adapted. Here in Indonesia, are we doing only hydropower? Are we doing a hybrid system, solar and hydro, for example? This needs to be properly considered when designing an electrification project. A data-driven approach, as I showed you earlier, if we do also demand-side analysis, we need to have a proper data when deciding which solution, and let us take the decision also based on the data and not by feelings or pressure or peer pressure from our partners. And the last point is again very important, and please keep that in mind, that we really need to involve the community where we are going to build the mini grid. Next slide. These points here probably address specifically when we come to independent power producer, one of the challenges which we also face in Indonesia when it comes to regulation. In Indonesia, we have a very strong state utility with PLN, and for independent power producer, the regulations are sometimes challenging. There are some there is some progress. There are some initiatives to also update the regulations, but this needs to be very carefully assessed at any given point if we plan a new system or a new mini grid, so that we don't face regulatory challenges or backlashes at the later stage of a project. And the last point, again, it's on productive end use. If you remember that sustainability comes when people can generate income, very simple, then it's also already well managed from this lecture here. Next slide. Yeah, now mini grid, if we stick to the mini grid for a few more words, we have multiple generations of mini grid. We started, and this is also what we still see here in Indonesia from previous times. We have mini grids. They have probably a single source of energy, like a diesel generator or a hydropower plant, and they just feed into the grid. The second generation mini grid is if we have, for example, a diesel or a hydropower plant, and then we add other renewables like wind or PV. So we already have a hybridization of our mini grid. And third and fourth generation is when we bring more data in it. So if we start to have automatic metering, data collection on consumption, etc., we're in the third generation. And the fourth generation is then when we have a kind of a fully digitalized mini grid available in place. Next slide. This graph here probably indicates you a bit more the application. And I would say in most cases these days, if we consider a mini grid, a third generation mini grid, this is in many cases the best option here in rural areas in Indonesia and elsewhere. As for fourth generation mini grids, we have a much higher investment. And we also need to remember that with a mini grid, we can also generate jobs for operators, etc. And in a fourth generation mini grid, then we again need less people to operate it. Next slide. Yeah, these are the barriers I already spoke about. So regulations can be a barrier for a successful mini-grid implementation, but also the tariff model, if it's not economic viable, you won't find any investor for a mini-grid, and therefore your project will never come to fly. Next slide. Next. Next slide, please.
Slide selanjutnya.
Oh, here we are. Very good. So when we look on the framework, and this is also what the government can do to create a more supporting environment. It's a lot on policy. So if you have a policy in place fostering a decentralized energy production, this is much more in favor also on private sector investment. On the other hand, but we also need to protect our clients, and therefore we need regulations in place. Regulation when it comes to quality of service, regulation when it comes to what are applicable tariffs, so that you don't have a community be just depending on an investor, and then this investor is dictating the tariffs. So here we need also a good regulation in place. Thirdly, also on environmental issues, and on license and contractual agreements. So it would be a wrong understanding to say we need to deregulate everything. We need regulations in place, but we need regulations which are set at the specific aim, and it's all based on the applicable policy. Next slide. So on the cost effectiveness, and you see here the blue area, and mini grids, as you see, mini grids are generally cost effective in semi-urban or rural areas where we have no access to a national grid, or where a national grid extension is too costly. Now here in Indonesia, the utility is very much investing in expanding the national grid. So the national grid comes to more and more areas, meaning that also the areas for independent off-grid mini-grids become less and less, which is based on the national policy, which is a good thing. So here in Indonesia, probably we need to look more into either very remote areas or then grid-connected hydropower plants. Next slide. Yeah, we have 3 more slides just on economics, and then we do a quick break. If we look here on the levelized cost of electricity on a global level, we see that hydropower is very competitive when it comes on the cost base. It's also more cost effective than fossil fuels. So in general, investments in a renewable energy, they normally pay off. Next slide. If we go down here to the ASEAN region, you see here as well the hydropower plant. Here you see the installed cost per watt. So you see that here in Southeast Asia, for let's say $2 investment, you can install 1 watt of hydropower plant, or we around $1,800 per kilowatt for a hydropower plant. O&M cost is somewhere around 1%, so we need about $18 per kilowatt per year for operation and maintenance. So that's probably the investment, the CapEx and OpEx side. And next slide, please. Yeah. if we look here also on the capacity factor, which is an indicator for the availability, so normally we use about 70% in average of our installed hydropower capacity. And here the interesting thing is the levelized cost at the end, and this gives you an indicator for the required tariff. So in most recent figures here for the ASEAN area, you see that the levelized cost of hydropower energy is somewhere around $5, meaning that's the overall cost per kilowatt hour produced or generated from hydropower plant. So, yeah. Next slide. Yeah. So if you agree, I would say we make a quick Q&A round and a quick break probably afterwards, and then we go here more into technical details.
Oke, baik ya, kita break dulu sebentar. Jadi tadi kita sudah membahas dua topik utama ya. Pertama dengan kegunaan energi air ya, terkait dengan air, ketersediaan air dan hubungannya dengan energi ya. Kemudian yang berikutnya adalah terkait dengan desain ya, desain untuk hydropower plant atau pembangkit listrik tenaga air. Nah sebelum kita lanjut ke sesi bagian yang ketiga ya terkait dengan technical design, mungkin silakan saya persilakan kepada audiens jika ada yang mau bertanya. Dipersilakan mungkin dari sebelah kiri dulu satu orang dan sebelah kanan satu orang. Silakan angkat tangan boleh? Oke, dari Pak Idrus boleh, silakan Pak.
Oke. Oh, ya. Enggak usah.
Ya, silakan Pak. Pakai bahasa Indonesia boleh, Pak.
Okay. In English. Okay. My name is Idrus Asgaf. I am from heavy equipment major. I have strong interest in micro hydropower system, and I would like to inquire about how to address water shortages that may occur during in dry season.
In dry season.
Yes.
Yeah, good question from Biders. Maybe you will answer it first ya. You will answer first. Directly answer. Yeah, during the dry season, how you manage the.
Yeah. Well, dry season is very challenging for hydropower because there is not much water available.
Yes.
We have to admit that we have to admit that we often think of we do a storage pond or a lake for dry season, but these lakes are never, they cannot be for a seasonal storage. They are for hours or for some days, but we cannot store or we cannot build a lake where we have water enough for, let's say, a full summer of hydropower production. So what we need to do when we know we have dry seasons with very little runoff in the river, we need to address this issue already in the design phase. So we need to have a proper hydraulic or hydrology assessment of our river stream and see how much water is available over a year. So specifically for medium or larger hydropower plants, we really need to do a hydrological assessment over a year, or we need to have data available from the past periods to then make a proper assessment of how much water is available or during how many months a year we can operate.
Okay, thank you very much.
Okay, thank you. May I recap in Indonesian? Okay, so saya akan tadi pertanyaan dari Pak Idrus ya. Jadi bagaimana kita memanage PLTA ya ketika musim kering ya atau musim kemarau. Jadi jawabannya adalah itu harus dilihat dari desain awal. Jadi memang ketika bikin PLTA itu pasti ada tempat penyimpanan ya, storage ya. Entah itu di danau atau di mana gitu. Nah itu penting untuk desain awal. Jadi kita harus tahu kira-kira berapa sih kapasitasnya. Itu jangan sampai ketika kita mendesain itu kita kehabisan air. Nah itu inti dari jawabannya ya. Oke, kemudian saya buka lagi untuk yang sesi kedua. Oke, yang pertama Mas yang baju dari energi ya, yang rambutnya agak keriting, silakan. Perkenalkan dulu mungkin namanya siapa?
Thank you. My name is Rajo Wibisono. My question is about realization about intersectionality in energy problem itu kayak including women's part in society, land usage in food production, terus kayak climate concern. All of those problems have more often than not have contradicting interest with economic growth in every area. Like, how do we as people who more educated in this problem convince people in rural area or just in general to convince them that this is like worthy problem to handle, like even though like it's not have immediate economic economic surplus. How do we convince them more efficiently? Thank you.
Oh, oke. Mungkin ini konfirmasi ya, Mas ya. Tadi pertanyaannya itu terkait dengan bagaimana kita meyakinkan masyarakat bahwa ketika kita bangun apa PLTA gitu ya, atau mikrohidro itu ada keuntungan secara ekonomi gitu ya. Ya walaupun tidak langsung. Oke, sorry about the economics ya. Impact directly on indirect.
Okay, yeah. How convincing the community? I think this social acceptance of a hydropower plant in the area where it's built is depending on a numerous of points. First and foremost, I think we need to convince the community that they will have an added value by having this hydropower plant within their area. What are advantages or added values for them? First of all, they have probably a better or a more reliable access to energy, and therefore they can produce more or have more parts of a value chain within their village, within their community, and therefore they can increase their income generation. So one of the winning arguments is often that the majority of the people in the village will, once the hydropower plant is operational, have a higher income than they have previously. Secondly, they have a higher quality of livelihood because you have a more reliable access to electricity. So you can operate all your appliances on a household level more constantly in a better quality. You have more light, you have more electricity for your appliances, be it a television, be it for cooking or whatever. So you can improve your quality of life by having access to a reliable and affordable electricity. So it's income generation, it's your own livelihood. And we also need to make sure that we do not create additional conflicts. So we need to have a clear picture of how this community is functioning and make also a risk assessment of who would have a negative impact in case we build a hydropower plant. So are there, I don't know, farmers who need to give land for a hydropower plant? Do we need to adjust an irrigation channel? Do we take water and then probably we need to see how can we irrigate a certain area of this village? So these are all topics which we need to address at the very early stage and come up with a clear plan and discuss it already from an early stage with the community. And then I think then we really create the good acceptance of our project.
Oke, let's saya mungkin sedikit rangkum tadi jawabannya ya, terkait bagaimana bisa meyakinkan dari sisi ekonomi secara langsung tidak langsung. Pertama ya, dengan adanya pembangunan hydropower itu akan meningkatkan nilai ya, ada added value. Salah satunya bisa dari income generation atau penambahan pemasukan. Kemudian juga tentu masyarakat sekitar itu akan memiliki akses energi yang cukup melimpah ya, cukup banyak. Misalnya tadi disebutkan bahwa mungkin buat entertainment, nyalain TV, buat masak dan lain-lain itu lebih mudah, tentu akan meningkatkan taraf hidup masyarakat sekitar. Dan yang tidak kalah penting adalah yang terakhir adalah jangan sampai dengan pembangunan ini akan ada konflik tambahan. Misalnya tadi masalah irigasi itu harus di-clearkan terlebih dahulu. Mungkin itu jawabannya. One more question? It's okay, one more question. Oke, one more question. Oke, tadi yang duluan Mbak yang kerudung biru ya. Untuk sesi ini, tenang, kita masih ada sesi berikutnya. Mungkin karena waktu kita terbatas, satu pertanyaan lagi ya. Oke, silakan. In Indonesia or English? Okay.
In English, please.
Yeah.
Okay. Thank you for the opportunity. I'm Yasmin from RASD class. So here I have two questions. First, it mentioned that water, energy, food, we need to integrate it from the three sector. And then also the fresh water will not same as the past. So it also mentioned that hydropower is the sustainable power plant. So my question is, could you please elaborate more about the engineering perspective regarding this matter? And then my second question, this is regarding the design. The climate exchange is causing the increase the earth surface temperature. And also it could be impact in the surface of the, I mean that it will be increase the water temperature. So based on this situation, should we consider making the technical adjustment to micro hydro power plant equipment in the future? So thank you.
Oke, good question. Ada dua pertanyaan. Tadi mungkin yang pertama itu terkait dengan perspektifnya Pak Thomas ya, terkait tadi yang masalah di awal yang dibahas terkait dengan water ya, about the water sustainability dan lain-lain ya. Kemudian yang kedua adalah terkait ini lebih ke teknikal ya, terkait dengan desain, kemudian terkait dengan survei water temperature dan ini tentang dengan technical adjustment-nya ya, bagaimana kita mengatur lah untuk desain. Okay, maybe you answer, please.
So I start with the second question on water temperature. For the hydropower plant itself, water temperature is probably of less relevance. Water temperature definitely has an impact on water as a habitat. So be it for species living in the water, be it for plants growing in the water. This definitely has an impact when water temperature is rising. So it's more, let's say, an ecosystem or a biological question or biodiversity question than for a hydropower plant. As long as let's say, the consistency of the water is not changing, then it shouldn't have an impact on our hydropower plant. It changes then if, for example, the chemical components start changing and when we become more salty, for example, because then we have higher corrosion. But in general, it doesn't change. And on the first question, it was on climate change, yeah? You need to help me again on that, yeah?
Yes, regarding the climate change. So my question is, we need to integrate about water, energy, and food. But in the other hand, in the future, maybe fresh water, it will be rare. I mean, the condition will be not the same as the previous. So it's also mentioned that hydropower plant is a sustainable power plant. So my question is, could you please elaborate more regarding the issue? In one hand, we have the fresh water will not the same as the previous, but how about the sustainability power plant?
Yeah.
Thank you.
Thanks. Yeah, climate change and hydropower, what we need to see, and this is probably a field of study also here in Indonesia, where I don't have data available, is how is climate change affecting the runoff of rivers? So if we have a change in precipitation, you remember I showed you the graph of where do we have rainfall on a global level? Is it more evaporation? Is it more precipitation? If we have a change on this, or if you have a change in seasonality, meaning that we have probably more rain or less rain in certain seasons, this needs to be addressed, let's say, on ecological studies on how climate change could impact in the future the runoff of river, and then we need to adapt. Meaning for us on an engineering level, if we do a hydrological assessment of a river and we have the river runoff curve over a year, and we know we build a hydropower plant with a operational time of, I don't know, 20, 30, 40 years, we then need to see, does climate change impact it or not? Now, for Switzerland speaking, I know we operate as well hydropower plants with my company who are on a river well, I have to say it other ways. In Switzerland, we have also snow and glaciers in the mountains, you might have seen. So this snow and glaciers, they provide somehow a seasonal storage of water. And if you have less snow and less glaciers, then your seasonal storage is reduced. Now, the hydropower plants I'm talking about, they are not affected by snow. So they just have whatever rain comes during a year. And there, for example, we find out that for the next 40 years, climate change will not drastically have an impact on the runoff. We will have dry days. We will have days with a lot of water. So there the fluctuation is not that much as for other streams who probably are more affected by snow or glacier. And the same is here in Indonesia. So you really need to have a look on the catchment area and on how climate change changes then the precipitation and the impact on the full catchment area.
Oke, ini agak panjang. Mungkin sedikit saya persingkat aja. Jadi tadi terkait dengan climate change, ya, terkait dengan keberlanjutan ya, terkait dengan fresh water, karena untuk PLTA itu butuh fresh water misalnya dari sungai. Memang climate change itu akan mempengaruhi salah satunya precipitation atau penguapan ya. Penguapan itu terkait dengan banyaknya air yang menguap dan kemungkinan turunnya hujan. Sehingga perlu ada di sini ada semacam hydrological assessment ya. Dan contoh di Switzerland juga terjadi misalnya banyak sumbernya itu dari glasier ya, atau dari es yang mencair untuk di sungai. Tapi secara umum ya, secara jangka panjang sebenarnya tidak terlalu berpengaruh banyak. Jadi memang seasonal saja. Nah, kemudian terkait tadi dengan pertanyaan yang kedua ya, water temperature tadi contohnya ada pengaruhnya ya. Tapi selama dia tidak terlalu berubah banyak ya, mungkin tidak akan berpengaruh terhadap equipment di permesinannya. Tapi mungkin secara biological mungkin ada ya pengaruh terhadap ekologi di dalam air tersebut. Mungkin itu jawabannya. Oke, now let's continue ya. Let's continue to the third session ya, about the engineering design. Okay, please. Yes.
So now comes the engineering part. We go a little bit more into design. I will provide you some technical slides, some formulas, and I will also indicate you what is to remember and what is just nice to know. Next slide. First slide to remember. This is our continuity equation, and you can imagine, you know the effect. Just imagine, and what is this slide representing? Just imagine you have a pipe, a garden hose or something, and you let run water through. And now you squeeze it at the end, and then you see the water comes out with a higher velocity. That's the continuity equation. meaning that the amount of water in a pipe, is always constant. You know, if you have water in a pipe, it cannot go anywhere else. So meaning if we have a large cross-section represented by the letter A, we have a small velocity. And if we squeeze our garden hose at the end, then the water comes out with a higher velocity. This is important to remember. So for all my dear fellow civil engineers, you should know this formula, this continuity equation. This will come every now and then again. And always remember the thing with the garden hose, if you squeeze it, then the water comes out faster. That helps you to remember it. I will come back to that later. Why is this equation relevant? This equation is relevant when it comes to selection of the penstock of the pipe of our hydropower plant, because the smaller we make our penstock, the higher the velocity is. And the higher the velocity is, the higher losses we have in the penstock. I will come to that later. Okay, next slide. And that's the Bernoulli equation. That's also important to understand. And it reflects that at any given point, we have three components of energy. And that's also why when we talk of renewable energy, that's why you have here on the compound an energy conversion lab. And that's all what we do. Because if you imagine a piece of water, and I will show it on the next slide, at the beginning you only have potential energy, which is our first term here represented by Z. If we're somewhere in the pipe, we have also pressure energy, and if we are moving, we have kinetic energy. And that's the main components. And the only thing we do is we convert one form of energy into another. We cannot create energy, and energy is not lost. Next slide. Yeah, here you have it also visually. You see it here on the top left. Just imagine being a little rubber duck, yeah, swimming on that pond. Then you have only potential energy. And once the little rubber duck, you are sucked into the system, you're under pressure, and your rubber duck, you try to expand yourself, so you have pressure energy, and you're moving, you have kinetic energy, but you're still not on the bottom, so you still have potential energy. And here at the very end where you get out, there is no more pressure energy, you still have a little bit of potential energy, and the rest is kinetic energy. So that's energy conversion, what we do. And imagine if we add here at the very end the turbine, and then we convert your remaining kinetic energy into mechanical and then electrical energy. So if we look at this slide, please remember, and this is one of the fundamental principles, energy cannot be generated, energy cannot be lost, energy can only be converted from one form into the other. And if we look on the next slide, please. Yeah. And if I say here we have losses, well, these losses is not that energy is lost, but there's just a part of originally potential energy, which is converted into thermal energy. These are the friction losses in our system. And that's nothing else than if you rub your hand, then you convert mechanical or kinetic energy into thermal energy. And that's the same what happens here in the system. So, but the total amount of energy is always constant. It's just a question of how is it distributed on the different fractions. Next slide. So this is our power formula for hydropower plant. And that's how we convert it. So you see here in the middle, actually our power producing is the product of the density of water multiplied with our gravity constant, G, multiplied with the amount of water, Q, and the head and the efficiency. And you see the units below in gray. Next slide, please. When we talk of losses, and that's actually where the losses or where thermal energy starts to happen. You see, we have our gross hydraulic power, that's at the top system, that's the maximum we can have. And then we have a number of losses, be it hydraulic losses, turbine losses on the generator, or then on the transformer. Next slide. Oh, what happened to that slide? Oh, sorry, there we have a layout problem, but it's the same formula. So again, here our power formula is that the power is equal to flow multiplied with the head, the density, and the gravity. And if we simplify our lives and assume that water has a density of 1,000 kilogram per cubic meters, we can even eliminate our density component and then just use the short form version, and then we have the power in kilowatt. This is definitely the most important formula to remember. P, the power, is equal to the product of the flow, the head, the density, gravity factor. What else do we have? G and the efficiency and the head. So, and that's a formula you really need to remember if you talk hydropower. This is a formula you should know by heart. That's, if you understood this slide, then you understood hydropower. Next slide. So we're now coming a bit more into technical details, as we have a lot of engineers here. We're not talking socioeconomics. So penstock, and I showed you the continuity equation. Now let's have a bit closer look on the pipe. Next slide, please. Normally, when we need to do a penstock sizing to find out how big does this pipe need to be, how do we define this pipe? Normally, we know what is our flow because we did a hydrological assessment and we made an assumption of how much water is available for a hydropower plant. This is somehow given. And we know from the topographic survey, we know the gross head. So now we need to find what is the diameter, what is the wall thickness, how are the specifications of our penstock. Next slide. And that's the process of how we do it. Now, in the blue box, the velocity, and I showed you the relevance of the velocity already in the continuity equation. The velocity defines also the cross-section of our pipe, depending on the flow. And as a good rule of thumb is to have a velocity somewhere between 2.5 and 3.5 meters per second. If we are above 3.5 meters per second, the losses in the pipe are just too high. We lose too much energy, which is converted into thermal energy. And if we are below 2.5 meters, then the diameter of, or the size of our penstock becomes very big, and then it's just not cost effective anymore. Big pipes are more expensive. So we choose a velocity, then based from the velocity, you see the formula, we can calculate the cross section. And then once we have our penstock, we can cross-check it by calculating the losses in our penstock. Next slide. A very easy form to determine a potential size of our penstock is just graphically. So you see here a potential chart where we can have our flow on the left-hand side. And this is now for an area where we have only certain diameters available. 12-inch, 14-inch, 16-inch, whatever. So if you're in an area where you have only certain types or certain sizes of pipes, you can easily do it graphically like this and say, okay, I have 600 liters, I have this 19-inch pipe available, so therefore I'm somewhere around 3.3 meters per second. Next slide. We can also do it the other way around, that we say, okay, we accept 3.5 meters per second. We have our 600 liters again. Therefore, we need something around 45 centimeters of diameter for our penstock. So this is a graphical solution to select the proper penstock. Next slide. Now, once we selected our pipe, we need to calculate the losses. And if you get my message here, please, we need to remember that the losses go always by the square of the velocity. So you can imagine if we double the velocity, if we use 4 meters per second instead of 2 meters per second, then the velocity, they will go by the factor of 4. So the higher the velocity, even more higher the losses will be in the pipe, because the losses, they go by the square. And you see here on the formula for the continuous loss. The continuous loss is just because you imagine if you again this rubber duck and you go into the pipe and you hit the wall, then you will scratch along the wall of this pipe, and these are losses. And this continuous loss, we can use the formula as you see here. We have a friction factor which we need to determine graphically. We have the length. So the longer the pipe, the higher the losses are. We have the diameter, and you see this term, the square of the velocity divided by 2g. And that's exactly why this velocity is so important. To reduce losses, we need to maintain a certain speed in our pipe. Secondly, we then have also different elements in our penstock, be it a valve, be it a bend, be it the bifurcation, be it the inlet or the outlet of our pipe. And also there, we do have losses in our system. But first of all, how do we come to these continuous losses? How do we get the detailed figures there? Next slide, please. Now, sizing of our penstock, we first need to determine the roughness of our pipe. As mentioned, it depends on the material. If you have an all corrugated steel pipe, you have a much higher roughness and therefore more higher losses than if you have a nice HDPE pipe, which is very smooth and you have less losses there. So there are tables for different materials, and you can determine the K value for your specific pipe. Next slide. And please click 2 more times so that next. Thanks. Here. Okay. So how are we doing it? Now, this is the so-called Moody diagram, and this you need to calculate the losses. So first of all, we have on the bottom axis, as you see, this is 1.2 multiplied with the flow divided by the diameter. If you have this is a simplified Moody diagram. There is the more scientific version as available, and then you would have the so-called Reynolds figure on the horizontal axis. So those who had already some lectures on hydraulics, if you know the Reynolds figure, that's literally the representation on the horizontal figure. Then you see this these curves. These are indicated the fraction from the roughness value divided by the diameter. You see here again this K value, that's what we need. And from the Reynolds figure, we go vertical up to our curve with the relevant value. And then we go over horizontally to find our friction factor for the specific pipe. And here on the vertical axis, that's your value for F, as you saw in the previous slide. Next slide. Yeah, here you just see the comparison on the left-hand side. You have the simplified version. On the right-hand side, you have a graph with the Reynolds figure on the bottom. But the results at the end are the same. Next. Yeah, this is just for those who want to have more the scientific. I'm not going into details. Next slide. So turbulence losses. As I said, we had the continuous losses, and then we have turbulence losses in different elements on in our penstock, be it a bend, be it a valve, whatever. And we quickly look at those as well. Next slide. Now, if we have an expansion, we have a small pipe and suddenly go into a big pipe, you can imagine that we have some turbulences here where it is expanding. And these turbulences, they create losses. And these losses we can again calculate by the proportion between the two cross sections. And then again, you see our famous term here, the square of the velocity divided by 2g. So here again, you see the higher the velocity is, the higher the losses are in our pipe. Next slide. If we go the other way around, the contraction. Imagine again, you're the rubber duck. You're coming here on the big pipe and suddenly you need to squeeze into the small pipe. This creates stress and therefore we have losses there as well. Next slide. This is when we go from the forebay into the pipe. You can imagine we can shape this part in a nicely manner, or we can just leave it as it is. And you see here from the values, by having a nicely rounded intake, as you see here on the left-hand side, on the right-hand side, compared just to let the pipe come into our forebay here on the left-hand side, you can see we can already save 80% of the losses. So this has a real impact on your design, and that's again a task for our fellow civil engineers to have here an appropriate design and to reduce losses already at the beginning of our system. Next slide. This is how we can calculate losses in the bends, and you see here on the graphic, I just want to show you the graphic here. The black areas, that's where we have turbulences in a pipe. That's where we have losses. And as you see, the smoother the bend is, the smaller the angle, the lower the losses are in our system. Next slide. Yeah, here's some more additional information. And you see how it evolves, the bigger the curve is. Next slide. Now, if we have different type of valves, you can imagine if we have a spherical valve, if a spherical valve is completely open, and again, you're the rubber duck in our pipe, you wouldn't mention that there is a valve. If we have a gate valve or a butterfly valve, then you will notify that you just passed the valve because there is a reduction of the diameter, and therefore we have losses also for valves. Next slide. Bifurcations are stress as well. You know it every morning when you're here in Jakarta in traffic. Always when two roads merge or go in different directions, there you have a traffic jam, and the same is in a pipe. So also in bifurcations, we have losses, and here again they go by the proportion between the two directions, and again with our term of the square of the velocity divided by 2g. Next slide. So here's some general notes just on designing our penstock. When we do decide on our penstock and then we calculate the losses, they should be somewhere between 5 and 10% of the overall energy production. If we have losses higher than 10%, then our penstock is too small. This is specifically true for small hydropower plant. If you do large hydropower plant, then you definitely need to do a detailed economic analysis. Next slide. Now the water hammer, this is an interesting phenomenon. And we also discussed it in multiple trainings which we provided here. And here it's less on how to calculate it, but more to understand the principle. Now, as you see here on the graph, now imagine we have a hydropower plant and suddenly the turbine blocks, or suddenly the system is closed at the lower end. Now, what is happening? And now just imagine you and all your colleagues as little rubber ducks are going into the pipe and suddenly there is a blockage next to the turbine. No. Please go back one slide. Thanks. So what we have all the water is coming down to the turbine and suddenly it's blocked. And then we have a wave which is going backward because somehow this pressure needs to be released. More water is flowing in, and then you have kind of a backward wave up to the intake. And this is what we call the water hammer. And this is somehow we need to be able to release. And that's what you see on the third picture. This is really this wave going back, and this creates an additional pressure on the pipe. So we don't have only the hydrostatic pressure as you see on the top image, but we have an addition. We have an additional pressure from this backward wave in the pipe, and our pipe needs to be designed in a manner that also this wet water hammer is not making the pipe to burst. Next slide. So we can calculate actually this water hammer, and that's what you see on the formula here on the top. And you see this pressure head of the surge, and this comes on top of the static pressure, is a product of the velocity and this term here on the right-hand side. And this term here includes also the Young's modulus, and the Young's modulus is an indicator for the material. And on opposite, when we want to make sure that our penstock can remain safe when we have a water hammer, we can calculate the safety factor, which should be bigger than 3.5. So that means first, with the first formula, we kind of see what is the maximum surge or the additional pressure on our pipe from this water hammer. And with the safety factor, we then calculate actually the diameter, not the diameter, the thickness of the wall. And you see the wall's thickness is here in the D. Next slide. Yeah, here are some values for the Young's modulus and the ultimate tensile strength, depending on different material. And as you can imagine, in that case, steel is much stronger than plastic. Next slide. So that was on the water hammer. There are you can, for these formulas, you can create Excel spreadsheet files. The professors who had been in our trainings from RESD, they have received these Excel files. We distributed it in the trainings, so you can use them exactly. Now, for some of you, it might be surprising, but if we look on a penstock, the pipe itself should be flexible. And this sounds probably strange for a massive steel pipe. But if I say it must be flexible, then I mean it must be flexible in a longitudinal direction. Why do we need this? Just imagine we have probably the power plant is turned off and the nice bright sun from Indonesia shines on that pipe. The pipe becomes hot. and suddenly we bring cold water because we put it back on operation. And then this cold water in the pipe creates stress for the material, and that's probably now more for the mechanical engineers. And you know, even iron can expand or contract a little bit. And this expansion and contraction we somehow need to adapt in our design, and therefore the penstock should be able to be flexible, at least in the longitudinal direction, so that we can compensate this contraction and expansion due to changes in temperature. Next slide. So this is a typical penstock alignment, and you see here we have some blocks, supporting blocks or supporting piers where the penstock is just placed on top of it. And we have some anchor blocks which really hold the penstock in position. And if you look at this graph and then you think, yeah, but just before he said the penstock need to be able to adjust to contraction and expansion. And now we place it somewhere fixed into concrete blocks. Then you need these elements between the concrete blocks, the so-called expansion joints. And an expansion joint is specifically an element in the penstock which can compensate for contraction and expansion of our penstock. So that means if we have one anchor block here and one anchor block here and the pipe in between, then we need to make sure that we have an expansion joint between these anchor blocks so that our pipe can expand or shrink a little bit. Next slide. Now, finally, on the penstock somehow on the top comes into a 4-bay, and there it is important to place it low enough. If we just place the penstock as you see here on the right-hand side, then if the water level drops a little bit, then we might have air into our system, and this reduces the efficiency. So whenever you design a 4-bay and the connection of the penstock, make sure that the penstock is at least covered by water 3 times its diameter. Next slide. So we have our penstock, and the penstock and then the turbine, that's a closed system. Now the question is, before the penstock, after the intake and before the penstock, we have water, but probably we have more water than fit into our penstock. And how do we get rid of that water? And for this, we have spillways. Spillways are a very important safety feature in our hydropower plant. And we can calculate it with that formula. I come to that formula in a minute. Next slide. Here again, we have some coefficients for the shape of our spillway, of our structure, which is overflown. Depending on the literature, depending on which type of formula you use, you have different values. Here are some given. Next slide. Yeah, and that's actually the full formula. You might find it in the literature as Polanyi formula. Just to give you the full context of the formula. You see here in the picture, you see a weir which is overflown. The weir has on both sides, it has a limitation, a retaining wall. Therefore, the value B is the width of the crest. So that's the amount of the water between these 2 retaining walls. H is how much water is on top of the weir. And then you have the flow coefficient for the structure. Next slide. So here you have some values again for this flow coefficient. And the value Q, the flow, is actually how much water is flowing over the weir. Next slide. So here again, you see sometimes in engineering, you have a rule of thumb. a simplified formula, and you have the full-fledged formula from science derived. And here you have the comparison between the two formulas. Next slide. Here's the same. Okay, next slide. Now, a spillway, as mentioned, and you saw it in the formula, the amount of water flowing over a weir is also depending on the length of the weir or of a spillway. And you can imagine if we have only a limited space of how much water can overflow a weir, because we have a channel. Imagine you have a channel, then probably your water can only rise by 10, 20 centimeters before it's overflowing everywhere. So we need to maintain sure that if the water level rises, our spillway probably only by 10 centimeters can evacuate all the water, which is too much, in a safe manner. And this might require then a very long spillway. And then there are some nice engineered solutions, like, for example, this piano key, which you see behind, which is somehow a folded spillway. And you see it's overflowing all along the spillway, or as you see here in the plan, this is all along this piano keys. Next slide. And if you see here, we actually need, and you see it on the plan, the length of the size of the weir here, it requires about 5 meters of the channel. You see this 4.93, that's in meters. So the length is 5 meters, but the total length of our weir, because it is folded, is almost 18 meters long. Meaning that we can disperse here about 12 cubic meters per second on this weir. And you can imagine if we would just do a straight spillway with only 5 meters, we would have only about a third of it. So here we can spill 12 cubic meters instead of only about 4 cubic meters if we would have made it straight. And there are different solutions. This is a piano key weir. There is, in literature, you find, for example, a morning glory weir, which is a nicely round shaded weir. So there are different solutions also in the literature available if you have limited space to increase the length of your weir. Next slide. And as a last hydraulic structure, we want to talk about the intake. And I think the intake is, in many cases, also the masterpiece of civil engineering, where we really need to make sure to have the water available in our system, but only the water we need and not too much excessive water. So here you see some potential intakes. In rural areas, these intakes are often very simple made, sometimes even only temporary structures, because in the flood season they will be destroyed, or it would take a very large effort to secure it for flood season. And here in this case, you see they do just diversion with simple, either just put the gravel there or some simple structures to divert the water. And in flood season, it's washed away and then it's redone in spring again. Next slide. Here's some more intake forms. Here on the left-hand side, a very interesting form. This is a so-called Coanda screen, which means this is an overflown screen. It's a self-cleaning screen, and it's also very well protected from gravel on top of it. So you can protect this Coanda screen and then kind of just cut out the water you need for your system. Next slide. Here, this is just a representation of a Coanda screen in the mountainous areas, what it could look like. Sometimes you also need to bury it. As you see, the majority of this structure is all on the ground. You see the aerial picture, and on the right-hand side, you see the design of the whole structure. Next slide. Now, intakes. We should place intakes normally on the outside of a river bend. Why do we do it on the outside of the river bend? Because on the inside we have sedimentation, and then our intake just gets clogged with sand, with sediments, etc. And this requires much higher efforts than to keep it clean. So if we do it on the outer side of the river bend, we somehow have a self-cleaning intake. Next slide. We can protect our intake with boulders, etc. So this is really then depending on the location where you do it. But often you see what nature has provided you to protect your intake and to place it on a naturally logical location. Next. Now, this is a very nice example for an orifice intake. And an orifice intake is the idea that your whole opening is underwater. And by placing it underwater, you can limit the inflow of the water. It's kind of a self-regulating system. Next slide. And that's what it looks like. So you see here on the lower image a cross section. You have the water level in the river on the left-hand side. You have this orifice underwater, and on the right-hand side, then you have the channel where the water is continuing, and you see you have a much lower water level in the channel. So this is this self-regulating feature of an orifice intake. How do we do it? We know how much water we need for our hydropower plant because we did the hydrological assessment. We came to a design flow, and therefore we know what the flow is. We set the velocity for an intake here, an appropriate velocity somewhere 1 to 1.5 meters per second, and then we get the cross section of our opening. Yeah? You see here again, that's the continuity equation from one of my very first slides. And with the cross section, we then can calculate, if we do a rectangular shape form, the width and the height. Next slide. So this is actually our formula for our orifice intake design, and you see the flow through our orifice. You see it there on the graphic. Is equal the product of the cross section of the orifice itself, a discharge coefficient, and then the square root of the water, of the difference between the two water levels in the river and in the channel. The importance is actually that our orifice is always submerged. Only then we have this self-regulating feature. Next slide. So how we do our civil design of our intake, we first do it for normal condition, and then we do the same calculation again for flood condition. And then when we know in flood condition of how much water we have in our hydropower system, then we need to size the spillway accordingly. Next slide. Yep. That's literally the process how we do it. We define the intake opening, we check the flow, and then we repeat it for flood condition and calculate the spillways right after our intake. Next slide. So I would like to give you an example because this sounds a bit theoretical, and let me walk you through a quick calculation example. an intake we built in Afghanistan, but hydraulics are everywhere the same. So what you see here, this is the design cross-section of our channel, and we need to bring water into our system here. The design flow, which was given from the initial assessment, is about 1 cubic meter per second. Next slide. Now here you see some designs. You see the normal water level, NWL, which is about 1 meter above ground. And in flood condition, we have another 60 centimeters, 600 millimeters of water. So in flood condition, the water is about here. And in normal condition, the water is about here. Next slide. So you see here with our formula, I can calculate the cross section of our opening, which I need. I have all the figures I need. I have our flow, 1 cubic meter. We have the water level as by design in the river. We have the sizing of our channel, so we can calculate the opening. What you see here, the engineer here added a 15% margin, because as you can imagine, if you're in areas like rural Afghanistan, probably civil engineering works is not so accurate as it could be. So we need to have a certain margin, maybe make the opening a little bit bigger in case that the work is not done perfectly well, that we still have enough water in our system. That's why we add this 15% margin. And with this formula, we calculate that we have almost a square meter of cross-section required for our orifice intake. Next slide, please. Yep. So we have the channel on the backside, as you see here from the cross-section, is 1.8 meter wide. So it is a fair assumption that our orifice opening has the same width as the channel. And then with the cross-section, we calculated is 0.88 square meter. We can then calculate the height of our opening. Okay. So that means we need an opening of 50 centimeters high and 1.8 meters wide. Next slide. And now we can do the same thing for flood condition. Now you see what happens now in flood condition. We have a much higher level in the river. We have now 1.6 meters. And first of all, we can assume in the first calculation, we can assume that we have an unchanged water level in the channel. This is just an assumption for a first calculation. Let's assume that no matter how much water we have in the river, we always have a constant water level in the channel. And then we can calculate, using our formula, how much water would go through our orifice intake. And you see here, this ends up to this 2.2 cubic meters. If our assumption would be correct, that we don't have a change of water level in the channel. Next slide. Now, yeah, that's what we did. So we calculated the water in our channel, and then we also go back to our channel and see how high would the water actually be in our channel if we bring in 2.2 cubic meters per second. Because as you can assume, if we bring 2 cubic meters instead of 1 cubic meter, the water level in the channel would be much higher. Next slide. So this is a bit of trial and error exercise. You can try it yourself in an Excel spreadsheet. But you will find out that the water level in the channel, which 2.2 cubic meters per second, would not be 70 centimeters, but it would be 1.1 meter. So we see our initial assumption that no matter what the water level in the river is doing, we have a constant water level in the channel is obviously wrong. So we have now a first assumption that if the water level in the river goes up to 1.6 meter, our water level would rise to 1.1 meter in the channel. Next slide. And now we do an iteration. We go in circles, as you see. Because now we have a new water level in our channel, yeah? We calculated 1.1 meter. So now what we do is we calculate how much water is now going through our orifice intake, because we still have the 1.6 meters in the channel, in the river, but now we have 1.1 meter in the channel and not only 73 centimeters. So we calculate it again and then we see, oh, but if this is the case, then we have only 1.7 cubic meters going through our orifice intake. And as you can assume, with 1.7 cubic meters, the water level in the channel would be a little bit less than 1.1 meter. And therefore, we do a next iteration. Next slide, please. And as you see here, with 1.7 cubic meter, the water level in the channel would not be 1.1 meter, but probably only 90 centimeters. So we are now already in the second iteration, and we can cross-check this result again. Next slide. Yeah, and here we see with 90 centimeter, then it's not 1.9 cubic meters, but probably 2 cubic meters. And you see this iteration now, after the third iteration, it slowly narrows itself to an end. We can do 3 iterations, we can do 5 iterations, but you rather quickly see that it comes to, it approaches a certain value, yeah? And here now with the 2 cubic meters, if you go to the next slide, please, then you see the water level in the channel would be somewhere around 1 meter. And you see already the results. Our first assumption brought us to the result 1.1 meter in the channel. The second result brought us to 90 centimeters. And the third iteration, we are at the average at 1 meter. So you see, it's a fair assumption after 3 iterations to stop it here and say, okay, in a flood condition with 1.6 meters in the river, we might have 1 meter in our channel. Next slide. Yeah, and then we can do the final calculation, and then we see that we will have about 1.85, 1.9 cubic meters in flood condition in our channel. And therefore, we then can calculate or design also our spillway, because we don't need 1.8 cubic meters for our hydropower plant, but only 1 cubic meter. Next slide. Yeah, that's the spillway calculation then as a recap from previous slide. So you see the design flow, you see the flood condition, how much water would enter our system in flood, and therefore these 800 liters we need to dispose in a safe manner. Next slide. Yeah, I have just, that was the engineering part, and for the remaining few minutes, I think we have a few more minutes, yeah? 5 minutes, okay. So let's use these 5 minutes and talk economics. I don't know, do we have economic experts in this room? Any economic students? No one. Nobody cares about economics. Okay. So be happy if you get a salary without economics. Next slide, please. That's the cost revenue timeline. That's important to understand. Hydropower requires a high investment at the beginning, and it has a long operation time. So the question is, when is the cutoff point or the break-even point when we have all our investment back in, and when do we start earning money? So, and you see, the longer we can have our operation, the more money we earn at the end. Next slide. Now, this is often a question of what is the average cost for hydropower or small hydropower in Indonesia. And you see here from the size in kilowatt towards the cost, and you can imagine the bigger a hydropower plant, the lower the cost per kilowatt are, because you have a certain economics of scale. and you can produce it cheaper. And at the end, the turbine for 20 or for 30 kilowatt is more or less the same price. But if you can install it for 30 kilowatt, the cost per kilowatt comes down. Next slide. So here you have average investment costs for Indonesia, just that you have a range. These figures may vary depending where you are. This figure may vary on the value of the dollar, on the economics, but these are a good range for investment costs. Next. On the OPEX side, yeah, you have fixed costs. If you needed a loan, you have your annual fees for the loan you need to pay. You have insurances, etc. And on the variable costs is if you have expenses for services, depending whether you need a contractor or not. You need to pay taxes depending on your income, etc. So this is variable. Next. Here's some O&M cost, and probably you want to remember this, the last three one where you have an indication in percent related to the investment cost, what you need to put in your budget for operation and maintenance. History shows that whenever you have a shortage of money, normally the first thing people cut is operation and maintenance cost, and then they're surprised if your power plant is not running anymore after a short period of time. So please put operation and maintenance cost into your budget, nail it there and leave it there so you have always enough money to reinvest in your hydropower plant. Next. Yeah, that's the definition of net present value. I think as we have no economics here, we skip that one. Next slide. Yeah, that's the formula. We go also to the next. There are some methods like discounted cash flow calculation. You can go into details, but might not be that of relevance for you right now. So we go to the next slide, please. Yeah. Yeah, but you might see in the net present value and the internal rate of return, and this is actually the graphic solution of if you record the net present value for your project, then you can calculate the internal rate of return, and the internal rate of return is kind of an internal interest rate. So imagine the internal rate of return similar to if you go to the bank for a credit, what they ask you as an interest for the credit, and the same should be if you put in your own money, what is your internal rate of return? That's kind of your internal interest rate. Next slide. Yeah, that's just how you can do it. Next. So this is just to show you how easily you lose money by a hydropower plant not being operational. I just want to show you here from an example from 2 hydropower plants which we operate in Switzerland. As you see here on the system, on the graph on the right hand, you have a river, the main river, and then it diverts water into the first hydropower plant, and then the water is brought further down in a channel to a second hydropower plant, and then returned into the river. And we had the issue that the digital control system, the SPS, was down in the upper system, in the upper MHP, and then also in the lower MHP. And just to indicate you the losses we had due to this, you see on the next slide. Yeah, oh, these are the tariffs. Just it's about between 10 and 20 US dollar cents per kilowatt hour in Switzerland. Next slide. Yeah, and that's the calculation. And you see, just because these power plants were down for about a week, we somehow lost about 5,000 US dollars. Or at that time, you need to calculate it again, about 75 million rupees. And actually, the maintenance cost, if we would have done it in time would have been a fraction, you see. So, but people saved money on maintenance, and therefore we had a downtime in the power plant, and we lost much more money due to the downtime instead of replacing the components in time. Next slide. Yeah, and I think we just look on 2 more slides and then we come to a point, if you agree. Operation key performance indicators. 2 more slides, I think, for hydropower operation. Next slides. So whenever you are on the owner side, and some of you might then work at PLN or at an investor, and you own hydropower plants and you have people operating it, then there might be a question, how do we measure the quality of our operation and maintenance? And for this, we can use these key performance indicators. As you see here, for example, on power plant downtime, power cuts, so how long are the power cuts, for what reasons, etc., or on the availability factors. So how available is the power plant? You can have a KPI also when it comes to cash flow, so that you have a pure economic view on your power plant and you compare power plant 1 to a power plant B and see what is the cash flow. Or also on the levelized cost of energy. Next slide. And this is probably important to understand the capacity factor and the full load hour. So a year has 8,760 hours. And the question is, if we calculate the total production which we have divided by the capacity, this gives us the full load hour. And the hydropower plant, the mini hydropower plant, should have something between 4,500 and 5,000 full load hours. Otherwise, it's not properly designed and maintained. So that means about half of the year, your hydropower plant should run on the maximum capacity. And that's then the capacity factor. That should be around 50% for a small hydropower plant. So let's see what's on the next slide. Yeah, so we skip it here. There will be some more slides if we have a technical problem on how to do a root cause analysis, but I think in view of the hour, we close it here. I hope that I could give you some insights in design and operation of mini hydropower plant, and if you agree, we go to the second Q&A session. We go Q&A. Any questions?
Oke, kita langsung masuk ke seksi Q&A yang kedua. Mohon maaf karena waktu kita terbatas, jadi hanya ada 2 pertanyaan saja, quick question ya. Dari kiri kanan, yang kiri dulu siapa? Oke ya, Mas yang baju hitam boleh.
Please go to the last slide if possible, or video is good.
Okay, thank you. I'm about to ask about hydropower plant implemented with machine learning. So, wait a second. Could we implement machine learning in hydropower plant to manage power management system so it could give the energy supply on estimated demand more efficiently? Is that feasible or just give additional overhead? Because according to the McKinsey, the AI models have clear advantages over traditional spreadsheet-based analytic methods, like reduce errors by between 20 to 50% compared to the traditional analytic methods for predicting the energy demand. So yeah, that's my question. Could we implement machine learning in hydropower plant to manage power management system so it could give the energy supply on estimated demand more efficiently? Is that feasible, especially in this country, or just give additional overhead? Thank you very much. I'm sorry if my English bad.
Pertanyaan apa tadi terkait efisiensi ya?
Sorry, I didn't got it. Oh, sure, yeah.
It's about efficiency. No.
Sorry, it was not the English, it was really just acoustically. I heard it about double or three times up here.
I'm sorry. I apologize.
All good, all good. Okay, the question is about machine learning and on operation and maintenance. And yes, we definitely should use ICT in all stages of the design. We definitely use computer-aided design, building information models, etc., for modern hydropower plant design. So we have an integrated design already, maybe more for larger dams. Machine learning, KI, etc., in operation and maintenance is, for example, very relevant for predictive maintenance. You might have heard on predictive maintenance. So with nowadays ICT solutions, you really can feed in whatever data you have. You need to have the right data. You need to have quality data. But then you can use machine learning and AI, for example, for predictive maintenance, so that you have models, trained models, where you can predict which will be the next component to fail, so you can do maintenance in time, invest in the right components, and replace them before they fail and probably cause a bigger damage or power outage of your hydropower plant. That's probably the most common application of machine learning and AI in hydropower main operation. Yeah. The other thing is you definitely can also use machine learning and AI in the operation itself, based on if you're grid connected, for grid management, grid stability. When you know what is the weather prediction, you have other renewables like solar or wind who might feed into the grid. You have a hydropower plant, you have hydrological data, knowing what would be the capacity of a hydropower plant. So for grid stability, grid management, you definitely use also AI and machine learning to have better results in grid management.
Okay, thank you for the information. Yeah,
Okay.
that's enough.
Oke, terima kasih. Mungkin tadi pertanyaannya itu terkait dengan penggunaan AI dan machine learning ya dalam desain. Dan tadi jawabannya itu adalah untuk penggunaan AI dan machine learning itu bisa dipakai untuk PLTA, terutama untuk predictive maintenance. Kurang lebih jawabannya seperti itu, atau juga untuk masalah manajemen tadi untuk pengambilan keputusan bisa dibantu dengan AI dan machine learning. Oke, second question. Ya, mungkin tadi Mas yang baju hitam ya. Mungkin kalau pakai bahasa Inggris bisa agak pelan ya, karena ekonya agak bagus ruangannya. Susah ditangkap. Yang itu, yang diri itu. Ya, Mas yang belakang. Mohon maaf ya, ini hanya karena waktunya terbatas ya. Mungkin bisa pertanyaannya langsung to the point ya.
Okay, my question is regarding something more general as opposed to technicalities. Now, based on your experiences and looking at Indonesia's current situation in terms of its dependencies on finite resources, the fact that we are a developing country, and the ever-changing climate that we are facing right now. Now, which transition plan is more effective and sustainable in terms of profitability? Is it a large initial investment based on a quick transition to renewable energy within years or even a decade or so? Or is it a gradual and steady shift of investment and implementation across multiple decades? Thank you.
Nah, tadi pertanyaan terkait dengan investasi ya. Mana yang lebih baik, yang besar atau kecil ya?
Which is better, a large investment in a short time frame or a gradual investment frame with gradual implementations in the industry within multiple decades?
Do you understand the question? Okay.
Well, the size of investment, well, it depends on the hydropower plant you plan. What I definitely would recommend is, once you decided on a project and you got all the approval and concession and whatever also from the authorities, then not to prolong the investment. Yeah, as you've seen on the graph, The investment in a hydropower plant itself is the same whether you do it on 1 year or 4 years. But the question is, when do you have the point where you have recovered all your investments by the revenues, which takes more time with a hydropower plant. And therefore, we need to have a very cost-effective design over the life cycle. So not only a cheap design for construction and then you have problem in maintenance, but we need to have a proper economic analysis on our design throughout the life cycle, and then really do the investment in the beginning and then try to generate revenues. The other thing is, if you have the opportunity to go bigger with your hydropower plant, then rather go for a bigger investment in a bigger power plant because they're generally more cost effective. The question is, do you have access to the financing for larger investments? But if you have access to larger to finance for larger investments, then I definitely would go for bigger projects. They're normally also more bankable than this tiny off-grid small hydropower plants, which are more challenging to get also loans and grants, for example.
Baik, tadi pertanyaannya terkait dengan investasi ya, yang besar itu gimana, atau mau yang kecil-kecil pelan-pelan gitu ya. Jadi intinya adalah kalau mau balik modal gitu ya, perlu dihitung baik-baik ya, terkait dengan cost efektifnya. Termasuk dalam segi life cycle tadi ya, life cycle untuk pembuatan power plant-nya. Tapi kalau memang ada dana yang cukup besar, maka memang proyek yang besar itu bisa bilang lebih menguntungkan ya dibandingkan yang proyek yang kecil. Oke, Thomas, is this all for you, Thomas? So this all? Okay, can we conclude your lecture? Okay. Oke, thank you very much. So, jadi saya mungkin akan sedikit review sedikit di bagian yang kedua about the technical part ya. Tadi kita sudah melihat beberapa hal-hal terkait dengan engineering design, technical design. Salah satunya adalah penstock ya. Penstock itu pipa ya, pipa yang buat pipa bertekanan tinggi yang dipakai untuk mengalirkan air, dan itu perlu desain yang sesuai ya. Sesuai dengan kondisi, karena kita harus memperhatikan faktor-faktor kerugian atau loss-loss yang ada, seperti banyak tadi ada turbulence, ada karena permukaan, roughness, bending dan lain-lain ya. Kemudian juga bagaimana spillway ya, spillway atau tempat buat air itu meluap ya, kalau misalnya water levelnya itu melebihi kapasitas dari bendungan kita biar tidak rusak. Nah, itu juga perlu dihitung. Kemudian terkait dengan intake atau bagaimana air itu bisa dialirkan, itu banyak ya, tadi ada perhitungan-perhitungannya. Dan yang terakhir adalah terkait dengan faktor ekonomi ya. Di sini yang mungkin saya highlight adalah untuk membuat suatu hydropower plant itu ada beberapa KPI atau key performance indicator yang perlu diperhatikan. Salah satunya adalah yang penting adalah terkait dengan availability factor ya, bagaimana si plant itu bisa beroperasi dalam 1 tahun itu berapa persen. Itu salah satu hal yang cukup penting selain masalah cost dan lain-lain. Maybe that's all for us today. Thank you for Mr. Thomas Gross for the time. So please give a big applause to our lecture today. So now I will give back the stage to the main MC. Thank you very much.
Thank you, Mr. Pribadi, for moderating this session. Ladies and gentlemen, Before we close the guest lecture series of the Renewable Energy Skill Development Program, I would like to express my sincere gratitude to our speaker, distinguished guests, and all participants for your presence and participations. Your insightful contributions have made this program a resounding success. I am Naura, and it's been a pleasure to serve as your Master of Ceremony. Thank you and wassalamualaikum warahmatullahi wabarakatuh.